Okay, so welcome everyone to this morning session. So I will be the chair. And it's my pleasure to introduce the first speaker of today, so Nicolas Rogemar from Grenoble, and he will be speaking about emulating spin liquid physics with 2D lattices. Yes.
Thanks a lot. Okay. So maybe before I start, I would like to thank the organizers for this nice opportunity to come to this workshop and to visit PISA for the first time. And I have to admit, this is also the very first time I listen math talks. So it's quite an experience. So that's interesting. So I'm a physicist. Worse, I'm an experimentalist. And worse, I'm not doing or studying skyrmionic textures. And what we do is, I would say, potentially basic, but I will try to convince you that it's worth investigating. So I also realized, listening the different talks, that as physicists, we like to show images. So if this is kind of puzzling to you, or if this is not clear, please just interrupt me anytime. So the main idea of what we do is kind of summarized in that slide. So we fabricate systems using magnetic nanostructures, and the idea is to emulate the physics of spin models, certain spin models. So I was also realizing this morning that most of the time, as experimentalists, we do stuff, and then we like to talk to theoreticians, for example, or kind of to, for example, model what we investigate, or to confirm by theory what we can measure, for example. I kind of do it the other way around. So I like to dig in the old literature, some models, theoretical models, for example, from statistical mechanics, and I try to emulate those models. And sometimes those models, they are a bit crazy for experimentalists, in the sense that they have some kind of assumptions that are unphysical, and you want to know, for example, to what extent actually a real system does what can be predicted by some models. So that's essentially the philosophy of how we work in that field. So this is a first image. So what you see here is a topographic image of the type of system we investigate. So you have in red a magnetic element. We don't care about the composition. It's a ferromagnet, so it can be whatever, iron. It's deposited on a substrate in gray, and you have typical dimensions. So you see, for example, the length of the bars. So they have this stadium shape. So they are essentially rectangular elements. So you see the width is that's typical dimension. So 500 nanometers. The width is about 100, and the thickness is, say, 20, but it can be much less. So they are large enough so that we can easily image them in the lab, either the real topography or the magnetic information, but they are small enough so that there is no real texture. So essentially the magnetization is pointing along the long axis of the element. So everything is governed by the shape and isotropy of the element. So the magnetization is pointing either up or down, or left or right in this image, to follow the long axis of the elements. So in the end, it turns out that it mimics like an Ising variable. So it can be either +1 or -1. And then we organize those elements on a graph. And the idea is this. So this is, for example, the ground state you expect if you have Ising variables coupled antiferromagnetically between first neighbors on a square grid, okay? Basically, what you have is an alternation of black and white, or +1 and -1 values. Of course, we are not doing exactly that. We change a very tiny ingredient, and then the physics is completely different. And what I'm going to talk about is the physics of frustrated systems. We had a talk yesterday. And in particular, what we want to study is the physics of disorder in magnetism, so what we call spin liquid physics. And we try to emulate that with an experimental platform. So how to get frustration? There are two means, and I will essentially reformulate what was said yesterday. There are like either two means, either through the geometry itself or through the interactions that you can like select in your system. So one easy way is to keep everything the same. So everything is like this. You have eigenvalues, anti-ferromagnetic coupling between nearest neighbors, and you change the graph and you put it triangular, like yesterday. And then you don't have any order. So what was predicted like some time ago is that when you do that, there is no magnetic order as you cool down the system. So the system is first like a paramagnet at high temperature, and if you reduce the temperature, it remains disordered, even at 0 K. And it remains disordered, and the ground state is composed of an infinite number of configuration. So it's just changing the geometry of the lattice on which you put the magnetic element or the magnetic degree of freedom changes the physics drastically. But it has to obey some rules. So it's not like completely random. So it's not like a random disorder. And as was said yesterday, you can reformulate the way you write down the energy. And what the system does is actually to minimize as much as it can the energy or its energy on each placket of the system. So if you want to alternate the colors because of the odd number of corners on the triangular placket, you can have black, white, and then either white or black. So there is always one link or one bound that is frustrated. Another way of doing or getting some disorder and avoid magnetic ordering is to involve further neighbor couplings. So instead of having only the blue links with nearest neighbor interaction or showing nearest neighbor interaction, you can, like, again, go back to the previous configuration, but in that case, consider second neighbor interaction, okay? So in red. So now you want to couple the spins along the diagonals. And if the coupling strength, so in blue and red, J1, J2 are exactly the same, then you have some competition between the interactions. So if you want to alternate the colors, you can do it that way, but then you frustrate those two bounds and vice versa. I don't know. For example, here you're happy there, but here you are frustrated. So that's another mean of like getting frustration and then having a ground state that is massively disordered. And because of that disorder, and because of the correlations that exist in the system, there are some funny properties and sometimes very intriguing properties and interesting physics, at least for a physicist. And I will try to show few examples, just basically to give you a flavor of the type of phenomena we like to study. And our approach is to fabricate that and to visualize this physics in real space, potentially in real time, in an experimental platform. So we like to see, like by eyes, the physics we investigate. One message, because this is important for what we do. It sounds like we can have frustration with anti-ferromagnets only, but it works also with ferromagnets. So in fact, those two systems, so I'm taking again the square lattice with those J1, J2 couplings. You can put the spins, in that case, the Ising values, for example, is pointing out of the plane. So it's black and white. We assume that there is the values pointing in that direction. But now you can put those values along the diagonals of the square placket. And in fact, those two systems, or those two models, they are identical, in fact, provided that you change the sign of the interaction. So here you have frustration if you couple the spins in an anti-ferromagnetic fashion. So you want to alternate the color. If you put the spin into the plane, you get the very same thing, but you have to you have to consider ferromagnetic-like interaction. So you want to align the spins along the same direction. I don't know, for example, those two, or like to have like head to tail or tail to head configuration like this. So the main message is that it actually also work with ferromagnets. So that's a kind of puzzling in the sense that you have a ferromagnetic element, so something that sticks to the fridge. You couple everything in a ferromagnetic fashion, and in the end, you don't have any magnetic ordering. It's just not a magnet anymore. Everything is like a magnet, the interaction and the element itself, but in the end, the collective behavior of the system is not a magnet. I mean, not a ferromagnet. And this is important because this is typically what we will implement experimentally. So I just want to show you what the system does. So maybe first a kind of definition, even though a definition is not always easy. So we consider disordered states of matter that we call spin liquids. So spin liquids, they are disordered, massively disordered, but they do have strong correlations because they have to obey a local constraint. So if you want, the system is correlated at least to a certain extent. So the correlation, the spin-spin correlations, they actually are not zero, and they can be pretty strong, but they decay to zero at large distances. So this is a typical example on the triangular lattice. So same as yesterday, but with not XY spins, but Ising spins. What you can do is a Monte Carlo simulation to like study the thermodynamic properties of the system, of the model. So this is numerical. So here you have the temperature in log scale, and you have the correlations. So the correlations, so I'm showing you here schematics. So if you take, so it's only a portion of the triangular lattice. You have the full lattice, but this is only like a portion. So if you take one spin, the very first neighbors are there, the second neighbors are there, third neighbors are there, fourth, etc. And you want to know on average, if you have a spin up, what is the probability to have it up at a certain distance or down at a certain distance, and depending on the sign, you know this, whether the correlations are like ferromagnetic-like or anti-ferromagnetic-like. And you can compute that for like whatever you want. And essentially what you have here is what the system does. So at very high temperature, so the system is like highly fluctuating. And what you get is basically a random distribution of black and white dots on the grid, on the triangular lattice. You have no correlations. So this is what we call a paramagnet, or ideal paramagnet, or high temperature paramagnet. So it's just a random distribution of spins. But as you reduce the temperature of the system, at some point the thermal energy will be of the order of magnitude of the coupling strength. So you will have a thermal bath. So you provide thermal energy, and on the other side you have like the coupling interaction. So when they are like basically equal, almost, then the system starts. So here the system starts to develop some correlations, and the system will try to have this constraint, this local constraint satisfied everywhere in the lattice. So like 2 white, 1 black, or vice versa. And you see that the correlations now, they do something. But again, there is a large number of configurations you have here, and you never have like +1 or -1. So it's never correlated at long distances. And if you continue at larger distances, all those correlations, they slowly decay to zero. But the system is strongly correlated, even though it's disordered. That's what I want to show you here. A word about the ground state itself. So when we study magnetism, we usually consider that the ground state is well defined in the sense that it can be either up or down. And you, for example, study like we saw yesterday, the reversal mechanism for going from one state to the other. If you have an anti-ferromagnet, usually that's the same. Here, the ground state is composed of a very large number of states. And this pocket of containing all the ground states is essentially infinite, at least for a physicist. So if you consider all possible states, so imagine you have you have a grid, you have n spins, and we have an Ising variable, so it can be either up or down. So the total number of states you can consider is this. In some cases, it has been the number of ground states has been determined. So there is an analytical form for the number of ground states you have in certain system. So I'm showing you just an example. What is important is that this number, sometimes it also goes like an exponential. So of course, if you have like a system in which you like increase, like small systems, by the way. For example, a lattice with 200 spins or like 1,000 spins. So that's pretty small, in fact, compared to, I don't know, the Avogadro number you have in a real crystal. This is the number you get, the number of microstates you have in the ground state. So it goes like crazy very quickly. So I think this is typically the number of atoms you have in the universe. And this is the number of configurations you have in the ground state. And it can be like just crazy. That's an exponential. And this is usually unlikely, not unlikely, but not common in magnetism. It's common in frustrated magnetism, but not in nanomagnetism, for example. Another way of saying the same thing is that we are used to like 3 states of matter in general. So liquid, gas, and solid. In magnetism, that's the same kind of thing. So if you have a paramagnet, it's a gas-like or ideal gas. If you have something that is ordered at low temperature, it's like a crystal, a solid. And frustration brings liquid-like physics into the game. So a disordered-like physics, but in magnetism. Okay, so one thing I want to mention here is that for an experimentalist, as well as for like something that can compute things, it's just something that is out of reach. So you have to find means to characterize your system because you cannot count them all. And because of the fact that the ground state has to satisfy a local constraint, and the fact that the ground state is infinitely degenerate, then people have shown that there are like interesting properties that emerge from those systems. I'm showing you here an example. So this is again a picture of. So this is obtained with microscopy, electron microscopy. You see the magnets. So it's a top view. So you see again these elongated bars on a square grid. And if you want to be in the ground state, after you reformulate the energy term, one thing you can do is to minimize each term of the sum. And if you can do that, you are in the ground state if each term is minimized. And on a square grid, you have like 4 spins that meet at each like node of the lattice. And if this is 0, then for each lattice site or each vertex, you are in the ground state. Okay, so if you have +1, +1, -1, -1, all types of combinations. Yeah, good question. That's something we always omit. So here it's exchange-like, of course. In our systems, we mimic an exchange interaction, but it's not an exchange interaction. You see the magnets, they are like disconnected from each other. So they are uniformly magnetized, they emit a stray field, and all magnets interact through this magnetostatic interaction. So there is what? Yes, exactly. Yeah. So that's a good point. In some cases, the physics is well modeled by a short range interaction, and in some cases, we have to consider the full range, the full dipolar interaction between the magnets. So you have different types for like finding the ground state. You can have this type of configuration or that type of. So this is like anti-ferromagnetic-like. This is like ferromagnetic-like. And it's kind of the same as the Kirchhoff law in electrostatic, not in electrostatics. When you study electricity, you have like you wire your circuit. The current that goes in has to go out. Okay, so it's the same for the magnetic flux. So if you want to be in the ground state, the flux that is coming in has to go out. So it's the 2 in, 2 out rule, if you wish. And theoreticians, they have shown that under those conditions, then the ground state has specific properties. So it's not just a liquid-like systems. it's a system that has like weird excitations or interesting excitations. So this is the magnetic information. So here you don't see the magnetic element. You see the field, the magnetic field that is emitted by each node. So this is emitted some field, this is emitted some field, and that's typically what you see here. So I'm not going to discuss that, so you have to believe me. But when you don't see much, it's this antiferromagnetic configuration. When you see something a bit, it's this type of configuration. So we know that we are in the ground state because we know that we either have this type of that type of configuration, meaning that we do minimize the energy term. But you see, we have two dark, one dark and one bright spot. There, the local constraint, which is having this equal to 0, is violated. So we have, in fact, a local configuration with 3 spins pointing in and 1 out, or vice versa. So it's a source or sink of a magnetic flux. And in those particular systems, so these are excitations living just above the ground state. These excitations, they actually behave as classical analogs of electric charges. So they actually move freely in the system. They interact through a Coulomb interaction. So they want to attract each other if they have opposite sign, or repel if they have the same charge. So really like an electron, but of course it's an analogy, and everything is classical here. But there is no charge, so everything is magnetic. So it's a magnetic charge. So people have called that magnetic monopoles, or classical analogs of monopoles, of magnetic monopoles. So what's interesting is the physics of those topological objects. They are topological. The only thing you can do is actually create them or remove them by pairs. So imagine that if we could have some fluctuations, some thermal energy we could provide and just make a movie instead of a single image, we would see that spot like essentially like behaving like a random walker. And these two guys, they should attract. That's what is predicted. So we have like point-like deconfined charge quasi-particles for our excitations in our system. So just to make a link with nanomagnetism, in nanomagnetism, we are used to have like ferromagnetic domains, or antiferromagnetic domains, so something that is ordered. And then when you have two domains, you have a domain wall, and the domain wall is typically 1 dimension below the system you consider. So in 2D, the domain wall is 1D, or 1D-like. In our system, there is no domain wall. Domains and domain walls are basically the same thing, and the defects are point-like objects. And what is cool is that we can like see them in the lattice, so we can spot them and track them in space and time potentially. So I want to give you like I have to go a bit faster. I want to give you a quick flavor of what we do. So to have a spin liquid, so I will try to show you 2 cases. So this is the first case is on the square grid, the system that I introduced before. To have a liquid regime, actually this doesn't work. So it was proposed like about 20 years ago, but this is too simple and that doesn't work. And the reason why it doesn't work is that, remember, to have the liquid-like regime, you have to have the nearest neighbor and the second neighbors having the same coupling strength. And because of the magnetostatic interaction between the elements, in fact, this interaction is stronger than that one. Okay, so we favor at low energy, or at low temperature, we favor this type of configuration, and the ground state is ordered. So we retrieve like conventional paramagnetic, antiferromagnetic transition in this system. So the idea is smart, but it doesn't work. And it took some time to find strategies experimentally to realize the spin liquid physics. So if you consider the square system again, so this is just the schematics. So you have like spins on your grid. You have for each square placket, you have 4 spins that meet. So you have 2 by 2 by 2 by 2 possibilities. So that makes 16. You can draw them all and classify them. You have 4 groups. You have those that do not respect any rule at all, with all the flux coming in or out. This is high energy states. Then you have the few spots that I showed before, those with 3 in, 1 out, or vice versa. So they are excitations. And then you have other configuration. You have 6, in fact, with the 2 spins coming in and 2 spins coming out. So the local constraint. But experimentally, you have this energy scale. So this is high in energy, slow in energy, a bit slower, a bit smaller. And then this is the local ground state. And you can tile the entire lattice with this. So if you have this energy hierarchy, then your ground state is ordered and the physics is kind of boring. So the whole trick is to make it such that you do have, or you have the capability to have those states having the same energy to restore the disordered in the ground state manifold and have a liquid physics. And what we have done, in fact, is slightly more than that. We found a strategy to tune those 2 energies, so we can even probe some model of statistical mechanics. But so just the idea is this. So if this doesn't work, one thing you can do is to use micromagnetism, in fact. So you connect everything. So you make a full grid of elements. So everything is connected now, but you leave a hole at the center of this site. And changing the diameter of the hole actually changes the local energy of the system. And we can tune those 2 energy continuously by changing a geometrical parameter in our system. So that's what we did. This is a micromagnetic simulations. So one thing you can do is to compute the energy, the micromagnetic energy you have in those different configurations with 2 spins pointing in or out. But now this is like a continuous picture. So now I'm not considering the Ising spins, but I'm considering the full magnet itself. So it does have a magnetization distribution. And by changing the diameter of the hole, you can change the value, the energy of those configurations. So these are the 4 energies for the 4 vertex types. Again, type 4, 3 in, 3 out, or those with 2 in, 2 out configurations. And what is interesting is this. So there is a crossover between those 2 lines. So at some point, you can find a critical value of the geometrical parameter you can implement in your physical system, such that the energy of the 2 vertices are exactly the same. So you can, in principle, reach the liquid-like physics if you can tune the system there. Okay, so that's essentially, to make the story short, that's what we did. We had a full sample. On this sample, we had plenty of lattices of square grids. And each time we change the whole diameter. Then we take that system, we shake it, whatever manner, we shake it. So we force the system to reach a low energy configuration or approach the ground state. And then we image them all, okay? So they all had the very same magnetic history. And then we look at how they behave as we change the whole diameter in the system. And so these are experimental results. And you see that if you change the diameter of the hole, you have very different configuration. So what you have here is really, you don't see it, but you have arrows, Ising values pointing in one way or the other. If you have a large diameter, you have patches of the ground state. So it's anti-ferromagnetic ordered here with the other configuration there. So you can have either up, down, up, down, up, down, or down, up, down, up, down, up, like in an anti-ferromagnet. And these are domain walls, like conventional magnetism, but on a discrete lattice. And as you change the whole diameter, you see that it becomes a mess. And in fact, you can characterize the correlations you have in the system. And it's exactly what you expect in the liquid regime. So we do have here a snapshot, like a photograph of a spin liquid configuration. Okay, and we can have like, oops, we can have plenty of them and of course do some statistics. So we do have a spin liquid physics, and more than that, we actually have an emulation here of a celebrated model of statistical mechanics in which people have shown theoretically how you, but from a statistical point of view, how you go from such an ordered ground state to a liquid-like regime. But here it's completely done experimentally. We don't have temperature. Everything is done essentially on the table at room temperature. So but we do have a fictional temperature, and in fact we emulate a temperature by changing the diameter of the hole. So if you wish, we could have similar results with the Monte Carlo simulations, in which you have really like thermal energy, but here we don't. And if you compare the two, they look exactly the same. But in our case, even though we have no temperature, we emulate that temperature with a geometrical parameter. So if you wish, the temperature is expressed in nanometers in our case. And just to have a quick take-home message on that part, what we are interested in now is the behavior of the excitations. So in the liquid regime, so these are the real magnetic images, and these are the like kind of reconstruction of the configuration. The excitations, they do behave like deconfined quasi-particles. And if you go into close to the ordered ground state, you see now they are confined within the domain walls. And that's also something similar to what we have in nanomagnetism. Imagine you have like a ferromagnet. You approach the ground state, you have two domains, you have a domain wall in between. If you change, for example, the chirality of the domain wall, then you have a kind of singularity in between when you rotate within the domain wall. It's kind of the same here. So we have the domain walls. We change chirality when we have those defects, but those defects, they are confined. In the left image, they are confined within the domain wall. Here, they are completely deconfined. There is no domain wall. So there must be a transition between the two. So we are now interested in how the excitations actually behave as we go through the phase diagram of the system. And the nature of the quasi-particles, the nature of the excitations should change. But as far as I can tell, this is not known, neither experimentally nor theoretically. So we do approach this physics through an experimental platform. And quickly, to finish, I want to show you something like, again, like a bit counterintuitive. So I'm changing now the geometry. So I'm doing the very same thing, but instead of having a square grid, I have a Kagome grid. So a Kagome grid is basically a triangular lattice with all triangles sharing the corners, not the edges. So we can like do the same and have magnets like on the sides of this lattice. So it looks like a honeycomb lattice, but it is a Kagome. And what is predicted, so now that's also a bit to answer the question about the long-range interaction. Depending on what you consider, if you have this system, but with short-range interactions only, you have only two phases, a gas phase, a paramagnet, and a spin liquid. As soon as you turn on the long-range dipolar interactions, the phase diagram is predicted to be way more complicated. It orders in the end, because the long-range dipolar interactions lift the degeneracy between all the configurations. So in the end, it's solid, but there exists another phase in between the liquid and the solid. So the question is what it is. We are used to have like gas, liquid, and solid. So what is this phase between a solid and a liquid? It turns out that it is both. It's kind of weird situation. You have an Ising system. It's neither a spin liquid or a crystal. It's both. So I just want to quickly no. So one way to see that is to do numerical simulations. So you do Monte Carlo simulations on your Kagome lattice, and you can generate a large number of spin configurations. And what you can do is to average them all. Okay. So if you are at high temperature in the paramagnetic regime, if you average all the configurations you have at a given temperature, then you have zero magnetization on each side of the lattice, meaning that the probability to have a spin pointing up or down is like, it's the same. So you have no magnetization on the lattice sides on average. In the first spin liquid, so remember, so in this first part of the phase diagram, it's exactly the same. So even though the system is highly correlated, and even though it has to obey a local constraint, you do the same, you see nothing. On average, spins can be either up or down. Of course, if you go to the ground state, then you get 10 to the 4 times the very same configuration. So again and again and again. So what you see here is just the ground state configuration. So it's ordered. You have the unit cell, etc. Okay. So the question is, what do you have there? If you are in the second or in this intermediate phase, you have something weird. It shows some orders, but not entirely. So it shows disorder and a strongly disordered phase, but it does show on average a magnetic pattern, but it's not the same as the ground state. So it's not the same. And what is really puzzling is that if you look at the magnetic moment that you have on average on each single site, it's 1/3 of the total moment you can have. But remember, we have an Ising value, so it's either up or down. Okay, nothing in between. It's just 1. Here, on average, if you count the magnetic moment you have, it's 1/3. So somehow you have to admit, that's kind of weird, but your Ising value, which can be either +1 or -1, somehow is cut in 3 pieces. I don't know what that means, but that's somehow what it shows. 1/3 of that component, which does not exist, but 1/3 of that component leads to a magnetic order, and the remaining part contributes to a spin liquid phase. So it's at the system is at the same time static and dynamics. It's ordered and disordered at the same time, but that's not a phase coexistence. So of course, that's not just a glass of water in which you have ice cubes. So here I do have a solid and a liquid, but if I choose one molecule in the system, I know that it's either the ice cube or the liquid. Okay, here you have a collective behavior of the matter, and each single spin, each single element is at the same time an ice cube and a liquid droplet, if you wish. So it's a collective behavior of matter, and it does the opposite of what you expect. Remember, we have the spins pointing into the plane, so we are considering ferromagnetic-like interaction between nearest neighbors. And the local order that is favored is anti-ferromagnet. So it goes against what you can imagine. So this has been like predicted numerically, and of course the whole thing was to know to what extent this actually exists in a system we can design. I want to make the story short. It works partially, so to some extent, and the whole interest of this study is to determine to what extent it actually works. So we can have, so these are like experiments. Again, one of the trick was to connect the elements and to have a geometrical parameter we can play with to change the energy of the vertex configurations. These are like images. And in the end, we do the same. We compare Monte Carlo simulations with experimental data points. Everything fits on the curves, meaning that we do emulate or reproduce the physics that is expected at thermodynamic equilibrium. And the whole trick was to select the right parameters to just end up in this very narrow region in temperature in which we expect this behavior. But by doing that, we cheat a bit, or we cheat a lot, in fact, and we bias a lot the physics as well. So it's working to some extent. Let's put it that way. And there are some like physical reasons why it should not work at all and why it doesn't work, in fact. I'm not going to discuss that, but the nature of the excitations actually changes drastically in that type of system. And something you can do like theoretically has no physical meaning in a real experiment. So of course that cannot work. So the entire problem is to find a way to potentially emulate that type of physics and to see to what extent it works. So if I want just to conclude, one take-home message I want to give is that those systems we can fabricate experimentally, they are like we see them as experimental emulators of different types of model in frustrated magnetism, and in particular, a mean to look at the physics of classical spin liquids and what we call ice models. And with that, I would like to thank you for your attention.
Thanks a lot for your very nice presentation. Are there any questions from the audience?
Thank you. Very interesting research. Suppose I'm going to simulate a lattice, maybe square lattice or triangular, whatever, two-dimensional Bravais lattice. And suppose I'm gonna take best GPU on the market, and who will be ahead of your hardware implementation in the sense of how many spins you can effectively simulate in this analog machine or my program. So where I will, so how big is the scale of your device could be?
So the answer is that depends on what you want to do. So one thing you can do is to measure an average quantity. So then you can have like whatever, crystal, an infinite number. And then you add, for example, if you measure the average magnetization, you don't care about the size of the system. In our case, we want to have the configuration of the system at the level of single elements. So we want to resolve all spin configurations locally. So we can, so it's a matter of time. So 2000 spins, for example, takes an hour. If you want more, that gives you an order of magnitude. If I increase by 10, it will be a day typically. So it's a limited number of spins, but it can be thousands of spins.
Yeah. So I want to measure some thermodynamical quantities, correlations, of course, etc. So I know how to do it in the program. I'm just wondering who will win this analog machine or simulation.
Oh,
probably you can upscale.
Okay, but
how big can you? Yeah, how big?
Well, I don't know how to answer, but either you have a static image and then you have like large number of spins with thousands of spins and then you average. But something else we want to do is to have maybe a more limited number of spins, but make it like thermally active. So it evolves in time. So in the end, we want to do some statistics or correlations analysis in space on a large number of spins, but static.
Mm-hmm.
And then we want to like emulate some dynamics and see how the correlations evolve in time. And then it's another issue. So because then what limits the statistics is the dynamics itself, or the time you need to get an image. So you are taking essentially images, and then you cannot compete with.
Okay, I have very specific question then. Can you make a lattice of the size 10,000 by 10,000?
Yes, we do. Yeah.
Okay.
It will take a bit of time to image everything, but a matter of a day. Yeah.
Okay, maybe one more quick question, otherwise we proceed with the next. So it does not seem the case, so let's thank the speaker again. Okay, so welcome everyone to the second part of this morning session, and it's a great pleasure of mine to introduce Luca Briani, who will speak about energy concentration in a two-dimensional magnetic skyrmion model.
Thank you, Leonard, and thanks to all the organizers for giving me the nice opportunity of presenting here my talk in this very beautiful workshop. And yes, I would like to say something about energy concentration in a two-dimensional magnetic skyrmion model, both in the discrete and the continuum setting. And I also have to say that I'm not sure I will say exactly what Maria Stella said I would say in this talk, so apologize for that probably. And okay, this is briefly the outline of the talk. I will start with a small introduction, and then I will proceed with the analysis of the continuum energy. And in the second half of the talk, I will talk about the discrete model. And so let me start with the introduction. And here also quoting one of yesterday's speakers, I have to say that I mainly do this introduction to remember myself what I'm doing, because I'm not an expert on physics or on the reasons behind it. So I'll be probably very quick on that. Okay, we know that magnetization arises in magnetic alloys, or maybe in response to some external magnetic field. We know that everything here can be modelized within a variational framework, and this is exactly what we are interested in this workshop. And we are looking at magnetic skyrmions that are topological solitons. So let's say topologically non-trivial magnetic configuration that locally minimize the micromagnetic energy. And these are interesting also, as we learned in the past days, because they probably have very potential use on spintronics devices. Okay, so some more words on the mathematical model. So the micromagnetic energy for me will be something that modelizes a ferromagnetic thin film. So I'm looking at maps from R2 to the sphere S2, the normalized, which represent the normalized magnetization configuration, and the energy will be something like the Dirichlet energy or exchange energy plus some additional term. And in general, one is interested in looking at critical points of the energy within a fixed topological class, so prescribing the topological degree. Okay, these are pictures of the two different skyrmions with different topological charges. And for us in this talk, let's say the reference model will be that of a chiral magnet. So we have two additional terms. And the first one is the Zeeman interaction, which favors, let's say, a uniform background state. So I fix a vector n in the sphere will be the north pole of the sphere in this talk, and I penalize the distance square from that vector. And plus, you may have the Jarodzejski-Moria interaction that, as we now know, favors some spin of the magnetic configuration. Okay. And concerning instead the topology, you usually look at the following formula. So this is the Kronecker formula for the degree. You integrate 1/4 pi time the integral of u scalar product, the cross product of the two derivatives of the spin field u. And okay, it is super well known that if your map is regular enough and is constant outside some fixed compact set, then you can always compose your map with a stereographic projection. Then you have a map from S2 to S2, and you compute the Brouwer degree, and the Kronecker formula exactly gives you the Brouwer degree of the map. So it has integer value. And by nowadays it's also super classical that you can extend everything to irregular maps, so Sobolev maps, using, for instance, the Schoen-Uhlenbeck results that also Maria Stella quoted before. And in this seminar, I will also refer to the integrand in the Kronecker formula as small q of u, and this is the topological charge density that for us will be kind of a device to track energy concentration in some analogy with what is done in these papers that I quoted here, the paper by Gerard, Alberto Baldo e Orlandi, and Alejandro Cicalese in the discrete setting. Okay, so just to conclude the introduction, let's say all in all, what usually one looking at what one looks at is the minimization of this energy with a fixed value for capital Q of U as an integer. And of course, we now know after all the seminars that the main difficulty is the weak instability of the topological charge. And here is mandatory to quote all the main results in this direction. So first, there is this result by Melchior in 2014, who first proved the existence in the non-confined case, so having as domain the whole space, the existence of unitary degree minimizers. Then the paper already quoted by Montel, Muratov, Simon, and Slastikov for the existence in the confined case. Then we already listened to the very nice talk by Teresa Simon, who presented us the result in for higher degree minimizers in the confined case. And in that paper, they also studied some concentration of minimizers when the Zeeman term goes to plus infinity. True, yes, sorry for that. Okay, and okay, and then of course, if you take the case h equal to k equal to 0, then you are looking at harmonic maps, which are okay. Unitary degree harmonic maps are known as Belyavin-Polyakov profiles or Mobius transformation, and they are proved to be a stable solution thanks to the work by Verdun, Mantel, Muratov, Simon. Okay. So what I'm looking at is something like that. So let's say okay, let's start with the continuum setting. So let me fix some notation first. I fix a reference domain, which is omega, and is a bounded open set in R2. N will be, as I said, the north pole of the sphere. Calligraphic U of omega is the functional space, so is H1 log R2 valued in S2 with prescribed value outside omega to be equal to the north pole. And then I will, as I said, denote by small q of u the topological charge density, so the integrand of the Kronecker formula. Sometimes I will use also mu of u. And m of omega is the set of radon measures on omega. And okay, the energy we are looking at is the following one. So is the Dirichlet energy plus some the Zeeman interaction with a diverging term in front of it. So diverging Zeeman interaction and no DMI term. I will be back on this assumption in some slides. Okay, this is the energy, and let me do some very simple remarks about this energy. So the first one is the charge energy inequality. We already encountered it. So you basically take this quantity here on the left, and you compute the squares. So you do some very easy algebraic manipulations. You use the fact that you are sphere valued, then you get the last term on the right-hand side, okay? Then you rearrange everything, and you get once you integrate, you get the bound, which is the charge energy inequality, which, okay, is, we already heard about this bound, okay? So what we can say about from this bound is, of course, the following easy consequence is that if you take a sequence which is bounded in energy, then you have for free that your topological charge density considered as a radon measure, so as a density which multiply the Lebesgue measure, then it converges in a weak star sense to some radon measure mu. Okay, this is just using this charge energy inequality. Then what we can also looking at is some scaling phenomenon. So you take your map, you note, which is some map which is constant outside, let's say a ball B1, and has topological charge equal to 1. You rescale your map with some value lambda epsilon. So you basically concentrate like in a smaller ball. you scale your energy, then the first term is conformal invariant, so you don't change the Dirichlet part, and you have some scaling in front of the Zeeman term. And whenever your energy is your lambda epsilon is chosen to be such that lambda epsilon times epsilon goes to plus infinity, then you may concentrate on a single point, still having always the degree 1. So this is, of course, what one has. I mean, this is the very well-known fact that n topological charge is weakly unstable. Okay, in the limit. So one, let's say, we wanted in somehow to, as a starting point, also for doing the discrete analysis, we wanted to say something about the generality of this phenomenon. So we look at that in the literature for let's say, finding the right references, but we weren't able to find it, so we decided to run our own proof of the following theorem, which in the end is rather easy, so I also like to present this theorem, and especially stated in this form with the topological charge density. So we have a sequence of spin fields in our admissible class of maps, which is bounded in energy, then it converges, as I said, to some radon measure mu, and this mu is atomic, so it is a discrete measure with coefficients in the set 4 pi z. And of course, we can also state this theorem in terms of a gamma convergence theorem. So basically what you should do is to take this new functional, which is now going from the set of measure to 0 plus infinity. So basically the functional is plus infinity otherwise, and is the infimum of the energy on that spin fields that has that measure as topological charge density. And with this, let's say, formulation, you have the following theorem. So the functional gamma converge to the functional f when epsilon goes to 0. And the functional f is nothing but the total variation measure on if the target measure is discrete and plus infinity otherwise. Okay, so let me quickly do some remarks on this theorem. In principle, you could add also DMI interaction, and this is no difficult because you can simply basically run the Young inequality, and you easily deduce that the new energy, let's say the Kirill-Skyrmion energy, so the energy I am using plus the Jaruzelski-Moria interaction is bounding from above the energy that I'm using. If you assume that this constant here is positive, but this is like the standard also the standard assumption when you look at also at minimizing an existence. So whenever you have that quantity that is positive, then you can always bound our energy, and so get again your compactness results also for the full Kirill-Skyrmion energy. And then, of course, some parts of the theorem are trivial. So basically, the existence part, I already commented it, is just charge energy inequality. Then the gamma lim inf part is just the weak lower semi-continuity of the norm of our energy, and of the total variation measures, sorry. And the gamma lim sup inequality instead is just what you expect. So you take the optimal profile, the Belyavin-Polyakov profile, and then you rescaling it to get the gamma lim sup inequality. Okay, so let me instead comment a bit on the proof, on our proof for the structure of the limit measure. So basically, what you do is you cover the part of omega which contains some, let's say, anisotropy over the square root of epsilon with disjoint balls. Using kind of a Modica-Mortola trick, you can estimate the radii of the balls that are covering this part. And then in this part, you select those balls that contain some energy with a fixed parameter eta, which is not going to 0 when epsilon goes to 0. And so you can have only finitely many of balls with this upper bound on the energy because of your bound on the energy. And so you know that when epsilon goes to 0, thanks also to the lower bound on the radii, you converge to some to finitely many points, okay, in the sense at least of Hausdorff. And then you estimate what happened outside these points. So basically you run what you expect. So you take a test function supported outside the points. You use this multilinear property of the topological charge density. So the topological charge density can be decomposed like that with this term, with this Jacobian term. And you decompose your integral in these three terms using also integration by part. And so then basically you realize that every term can be estimated using the definition of the region that I covered. Okay, so for instance, in the blue term, U epsilon minus n, you know that by definition can be controlled because you have the upper bound on the anisotropy. The first integral instead is easy because you have just the first two components of the spin fields and the gradient term, so you can use the energy, the Dirichlet energy, to control it, and you control also the third term, so you get something like that. So let's say the first three terms are good because they are going to 0 when epsilon goes to 0. The problem could be only this last term, but there is, so exactly you want to compute in somehow this last term, but there you can play with the fact that you are inside the ball when a ball when you can control the anisotropy, and so basically you can do a cutoff argument, let's say an ad hoc cutoff argument, and using the definition of topological degree to know that every part has to be close to an integer, and playing a bit with this fact, you can get also this upper bound here, so you can control every term in this energy estimation. Okay, so now you know that basically outside finitely many points, your energy cannot concentrate. So the target measure in the end is indeed atomic. And the last part, of course, is to prove that the value of the measure on every point is an integer, and okay, 4 pi integer, and then this is again a blow-up argument, so a cutoff, and playing with the definition of topological degree. Okay, so that was it for the continuum, say, analysis, and this is exactly the result we would like to get also in the discrete part. So we would like to show how the topological degree can concentrate for a discrete spin field. So let's start again with discrete spin systems. So we know that magnetic systems can be, also discrete magnetic systems can be studied within a variational framework. Let me quote some result in this direction. So first there is this result by Alejandro, Brides, and Marco is here in the audience, in which they studied the Ising model, so ferromagnetic system on a Z2 values with -1 + 1. Then from the talk of Leonard now we know exactly what is going on for the XY model from Z2 with the value in S1. So basically the first result in this direction is the one by Alejandro and Cicalese, in which they prove some Ginzburg-Landau behavior for this model. And then, as Leonard explained us, also you can consider frustrated systems and analyze some phase transition phenomenon for this kind of XY model. So if you want, here we are looking at ferromagnetic systems as two-valued with Heisenberg model, so XY plus a large Zeeman potential. Okay, so the energy, So first, let me present the lattice. So for let's say interpolation region, is nice to consider the triangular lattice but it's exactly as you can take the square lattice and then choose a triangulation of the square lattice. This does not change anything. So with spacing epsilon, this is the lattice. Then you have your set of spin fields. So what is a spin field? Is a map from the lattice L epsilon with values on the sphere S2. And of course, you say that your spin field is constant outside omega, and this constancy, this outside has to be proper defined, but okay. So in the end, the spin field is something like that. Okay. And then the energy you are looking at is something like that. So you take the square distance between the values of the spin field computed on two nearest neighborhood, and plus you have the square distance of the value of a spin field from the vector n. So the first one will be the Heisenberg term of our energy. The second one will be the Zeeman term of our energy. Okay, so if now you proceed as also Maria Stella was doing by simply taking on each plaquette of the triangular lattice your affine interpolation, then you suddenly realize that your discrete energy is basically up to constants the Dirichlet energy of the affine interpolation plus the potential term of the affine interpolation. So exactly the continuum energy we were discussing in the first part. Here, the only caveat is that a priori is not, it comes not for free that the affine interpolation is S2 valued, which for us was, let's say, kind of an important feature in running the proof of the continuum theorem. And okay, and this is exactly also this was exactly a problem also in Maria Stella talk. So in somehow you have to deal with the fact that is not clear how to interpolate still having S1, still having S2 valued maps. And it's something that is completely different, for instance, from what Leonard was saying, because when you have S1 valued maps, then it's rather easy to find good interpolation. Okay, so first a remark about, because we want also to define some kind of topological degree for discrete spin systems. So let's have a look at something which is very trivial. So I apologize for for those who think that is too trivial, but anyhow. So this is the topological charge on the left-hand side. On the right-hand side, we have the usual Jacobian degree. Then we know that the map is sphere valued. For any map which is sphere valued, then you simply have this simple identity. Here you use the fact that you are sphere valued, right? Because then you can, they are orthogonal. Okay, so you have this identity. And then simply by the area formula which is telling us that like integrating the absolute value of the topological degree on a small area R gives exactly how many times the region, the image of the, it gives the area with multiplicity of the image through the spin field of the area R. Okay, this is super well known. So in somehow you want to do the same with your discrete spin field. Okay, so what can we do with the discrete spin field? And then, as we already known, we can basically rely on Berg-Luscher idea. So you can take a plaquette of your lattice and you map the plaquette of your lattice in the hole, so also the interior, in the geodesic triangle, which has boundary edges given by, which has vertex given by the values of the spin field on the triangular lattice. Okay. So usually, whenever you use Berg-Luscher method, you need to say something about antipodal configurations or about let's say degenerate configuration, which are most likely you won't find it. But we wanted to run something that avoid any let's say a priori axiom on this, and so we wanted to remark that, okay, of course, this is not possible whenever you have antipodal vectors. antipodal vectors are also points that are in a same like great circle. Okay, so what we cooked up in the end is something like that. So instead of looking at only at interpolation region which are triangle, we are looking at interpolation region that in principle could be some bit more complicated. So basically and we call it admissible interpolation region. So we have our triangular lattice, and we basically do the following. So whenever you have an edge which is confined between two antipodal vectors, and for which you don't have a well-defined geodesic, you put a dotted line. Whenever you have two vectors for which instead you can define uniquely a geodesic, you put a continuous line. And doing that, you then define connected and max connected regions, those regions that don't have dotted lines in the boundary, and maximal, of course, with respect to the set inclusion. So our admissible interpolation regions are exactly this kind of regions. So in the boundary, you won't find any dotted line. That means that in the boundary, you can for this kind of regions, you can always define in the whole boundary of the region the associated geodesic on the sphere. Okay. Then you look at some super easy properties of this kind of admissible interpolations region. The first one is the following. So whenever you have a region like that, you take the image through U of your region, and you find that in the sphere you have at most 4 points. And of course, the boundary of your region in R2 has a canonical, let's say, orientation, which is simply given by taking the canonical, the counterclockwise orientation of R2. Okay, so basically the whole boundary is well defined as a geodesic on the sphere. Then what you do is it is simply connected? No, it is not. Okay, no. No, it is not. And okay, it is not, but of course you can show that when it is not simply connected, then it cannot be whatever. Okay, that's the point. Okay, and okay, so we associate to every admissible interpolation region an admissible interpolation surface on the sphere. What it is the region on the sphere whose boundary is the piecewise geodesic oriented, as I said. Okay, with minimal surface area. Okay, then of course, this is of course not unique, but we can characterize completely what is going on there. So either you have an arc of geodesic, or you have a geodesic triangle, or you have the union of two adjacent geodesic triangle, or in the worst case, you have an hemisphere. And of course, whenever you get an hemisphere, you cannot decide what you do. So you have to take, you have to make a choice. Okay. So once we have this definition of discrete topological of admissible interpolation region, we can define our notion of discrete topological charge. So what is a discrete topological charge? You get your spin field epsilon, and you take an atomic measure, which is, and you say that that atomic measure is admissible for your spin field if it is of the following form. So if the sum of some Dirac deltas times some coefficient, and every Dirac deltas is centered at a point in the interior of an interpolation region, and every coefficient is instead the area of an admissible interpolation surface with the sign given exactly by the orientation that I defined for the interpolation region. Okay. So this is the definition of discrete topological charge. Of course, as I said, whenever you have this hemisphere, you have to admit that a spin field could have, in principle, has like more than one admissible topological charge. Okay, so we can prove that this is a good definition in the following mathematical sense. So if you take a bounded open set, you take your spin field, you have admissible topological charge for the spin field with the following form. Then you can first of all define an interpolation map with values on the sphere whose continuum energy is completely controlled by the discrete energy of the spin field, whose discrete topological charge enjoys the following identity. So whenever I compute that on an interpolation region, I take exactly the area of the interpolation surface with the right sign. And in flat norm, the topological charge density is close to the given mu, which is the admissible interpolation admissible topological charge, close in the sense that I can control it with epsilon times R energy. Okay, and once you have this proposition, you can basically run the theorem. So whenever you get a sequence of spin fields which are bounded in discrete energy, you can and you take a sequence of measures for which every measure is admissible for the relevant spin field, then that sequence of measure converge to some radon measure, which is an atomic measure with coefficients in 4 pi z. And in analogy with the continuum setting, you can also run the proof of up to technicalities due to the fact that you are working with discrete spin fields. You can run the proof of the energy concentration. So what you're doing is the following. You take your energy, you define your energy on the set of radon measures by saying that whenever you have an energy which is an admissible interpolation an admissible topological charge for some spin field, you take the infimum on the energies and plus infinity otherwise. And then this new functional, gamma converge when epsilon goes to 0 to some functional calligraphic E of mu, which is given by plus infinity otherwise and some kind of total variation measure of the target measure. Here, of course, you cannot, at least we were not able to completely characterize the limit that I guess would be very interesting, but the only thing we got in the end is some function psi, which is kind of a self-formula. So every psi is given by some optimization problem among discrete spin fields, which has a prescribed degree on B1. So you really have to solve some cell problem to completely characterize the gamma limit. And so that was basically it. So let me also summarize a bit what I did. So we studied concentration of energy for magnetic skyrmions in a regime when such a concentration is possible, and our energy was given by Zeeman interaction and possibly by Jaruzelski-Morier interaction, but the important things was that Zeeman interaction was diverging, and then we define a discrete notion of topological charge for maps from the lattice to the sphere, and we also characterize the gamma limit of our topological charge, discrete topological charges. So that was it. Thank you for your attention. And if you are interested in this, is on the archive you can find our work. Okay.
Thank you, Luca. Are there any questions from the audience?
Can you give me an example of a region that is not an admissible interpolation region?
That is not an admissible interpolation region whenever you have something like, so I don't know, you take, I mean, whenever you get antipodal points on the boundary of edges and you take something like, I don't know, take here U1, here U2, here minus U2. This is not interpolation region. So you continue and then you look at this one. Maybe this one is U2, so this is well defined, this not. Then maybe you go here and you find U3 and then you can close and this is your region in which you interpolate. So you want maps only this triangle, but the whole region in a square-like stuff in the sphere.
Okay.
Yeah, I'm so sorry. I wanted to.
Yeah, I was just wondering about your function psi of your cell problem. Do you have any estimates on it? Or?
Not really. I mean, this is exactly how the the function psi look at. So this is the only, let's say, the best we can do is this definition. But we don't know if it's homogeneous, linear, or we don't know yet. So we are trying to get some more information about it. But for the moment, we weren't able.
Heisenberg are comparable, right, on the discrete lattice. So psi, for example, if I put a constant in front of Zeeman, this psi would depend on that constant, right?
Yes.
Kind of
how this
minimizer of, you know.
Yeah, exactly. Is some discrete minimizer of exactly.
Okay. And there's no reason to think that this is somehow related to the continuum to Bilal particles.
I mean, yeah, there is no reason. I'm not sure. Maybe there is. Maybe we don't know. Yeah. Yeah.
You choose Zeeman a bit weaker but strong enough, then you can relate. I'm sure that you could relate.
Depends on which lattice you choose, for example. Is it true? You are telling me that if Zeeman is sufficiently weak and the lattice is triangular, you get this psi would be given by what, 4 pi?
Apart from the underlying geometry, I would be convinced. So because the end, like here, somehow you can. This is a non-negative perturbation, right? The Zeeman, but you can then construct competitors that let's say at the continuum concentrate at a scale, let's say eta epsilon, where you cover the sphere. So then the non-negative term.
Sure. So the psi should be less or equal than the continuum value, but maybe there are even better competitors.
Right.
Yeah.
And can you exclude them?
No.
Okay. For now, no.
Okay.
Thanks.
So, as personally for me, it seems interesting to give any kind of answer to the following question. It is purely about discrete versus continuum, because for discrete, actually, we can skip Zeeman, we can skip Zeloshinsky and take only exchange. And for exchange and for fixed boundary condition, we can find discrete skyrmion to be stable. It will not killed for the lattice. So, I mean, let's take lattice 10 by 10. I think it will be there, 100 by 100, probably. So, yeah, but I can compute, I see, I do believe it's pretty accurate. But it's a very big. So, yeah, that's I'm asking if we can prove something, because I know it do exists in comparison to in continuum limit. It doesn't exist. For discrete lattice, it exists, and the only parameter it is size of the lattice, which control it. So it's very big lattice, it will disappear probably. So can we say something certain about this?
Yeah, okay. No, not for the moment. I mean, yeah. What we wanted to try to do at some point is to try to really understand if at the point is convenient to get these antipodal configurations that maybe you mentioned before, then like in the self formula, if you can prove that you have to rely on some degenerate triangles instead of taking, that is, I don't know, maybe this is related to, but we weren't able for them all. No.
How do you define it?
Defined what? I can compute by Berk-Luescher, and it will give me -1. What's the problem?
Okay, Berk-Luescher, but what if Berk-Luescher, what if you are degenerate? What if Berk-Luescher is ambiguous?
This is probably the else case, but I will be satisfied with this case.
How do you know it exists?
I can compute it. I trust what my program showing.
It's the best.
This is second question. So,
are there any other questions? Doesn't seem the case, so please thank Luca again.
Thank you.
Okay, so the last speaker of this morning's session will be Lucia De Luca from Rome, and she will be speaking about the variational analysis for nonlinear elastic energy induced by edge dislocations.
Okay, so thanks, Leonard, for the introduction. Thanks to the organizers for this very nice workshop and for having invited me when they put related topics in the title of the conference, okay? So I will talk about something I started to work on when I was a PhD student, and then I tried to somehow to continue. And so the problem is the problem of edge dislocations that were introduced yesterday in the talk by Tristan Kren. And the results I will present are obtained in collaboration with the people listed here. Okay, so the dislocations, so I'm interested in nonlinear models, but I will start from linear models. And actually, I will start from what an edge dislocation is in my picture. Okay, so dislocations are, in general, one defects in the periodic structure of a crystal. And among the other things, they are believed to be the main microscopic mechanism for macroscopic plastic deformations. Dislocations are lines, so they can be loops or whatever. But in my talk, dislocations are straight lines that are orthogonal to the screen. So they are identified with points. Okay, and the edge here means that the Burgers vector, that is a measure of the edge dislocation, is orthogonal to the dislocation line. So if the dislocation line is orthogonal to the screen, the Burgers vector is in the screen. And in what I will present, I will adopt the so-called Lagrangian formulation, namely to see dislocations as consequences of deformation from a given reference configuration that does not exist. So the only thing that exists is the deformed one, but I assume to have dislocations, so they assume to have a reference configuration, and somehow to see the deformation that creates this defect. And for edge dislocation, the picture that one should have in mind is the following. So I start from a cubic lattice that once projected on the screen becomes a square lattice. And the deformation I want to consider is the following. So I take a portion of the plane and decide to move vertical half lines here by a small quantity at the beginning. So I take this half line and I move by 1/3 the lattice spacing horizontally. Then I take this half line here and I move it by 2/3. And then from the third line starting from the third half line, I move it by 1 lattice spacing horizontally. So this creates this strange face here. So all the faces becomes more or less squares. Okay, so they are elastically deformed, except for this face here that is trapezoidal. Okay. But what is the way? Okay, so this is the picture, but this cannot be adopted as a mathematical definition. So what is the way of detecting a dislocation? And the way that was presented in the talk by yesterday is by Kran yesterday is the following. So I draw a circuit that is closed in the reference configuration, and I try to replicate this circle in the circuit in the deformed one. Okay, so this is the Burger circuit. And now if I go somehow follow the same directions, then what I end up with is that the circle does not close anymore, and that in order to be closed, I have to come back by this vector, and this is the Burgers vector, okay? And this is a vector that lies in the lattice, okay? Okay, so what does this mean? This means that in this green circuit here, there is a dislocation that has this weight. And this defect is what I observe every time that I take a circuit that contains this cell. Okay? Then, okay, so this is the picture. So, okay, let me stress the fact that dislocations introduce the effect locally. Okay, so this means that if I draw a circuit in a region that does not contain this cell, then I do not see anything. The circuit closes both in the reference and the deformed configuration. Okay, so this suggests me how should I model this problem. Okay, so first point is the domain. The domain will be omega, that is a bounded subset of R2 that is smooth, simply connected, and whatever you want. A dislocation measure is identified with sum of weighted Dirac deltas, whose weights are epsilon, that is the lattice spacing, and times b, where b is a vector that belongs to a certain lattice. In the previous picture, it was zeta 2. And so this is the dislocation measure, and the dislocation measure is by its nature discrete. And the epsilon, okay, that appeared before is lattice spacing. And okay, epsilon is smaller and smaller with respect to the size of omega, and the goal of my talk will be to send epsilon to 0. And I denote by omega epsilon mu the set omega once I removed the balls that are centered at the singularities xn and with the radius epsilon. And I will call these balls core of the dislocation. So the idea is that far from so outside of this ball, the behavior of the material is purely elastic, whereas inside the ball is plastic. Okay, so we don't know anything. Okay, so these are the domain, and now we want to compute an energy. We want to define an energy here, and the energy is defined on some, so depends on some variable that is denoted by beta. Okay, that locally behaves like the gradient of the displacement. So the displacement is actually the function that moves the point from the reference configuration to the deformed one. Okay, so this, in case of perfect elasticity, can be done globally. In the case of edge dislocation, can be done only locally. And the set, so the strains that are compatible with the measure mu are given by those matrix fields that are in L2 of omega minus the coarse, that are elastic outside the course, so they are curve-free, and that satisfy the circulation condition that is here. That is the condition corresponding to draw the Burger circuit. So the circulation on the boundary of a domain contained in omega is given by mu of that domain. And now the energy I want to consider is an elastic energy. I start, as I said, from linear model. So the energy is the elastic energy here, that is described by a linear elasticity tensor C. And that's, since the problem is settled in the context of linear elasticity, is coercive only on the symmetric part of the strain. Okay, so usually when one has some elastic energy is gradient squared. In the case of linear elasticity, and this is something can be seen starting from the linear model, the coercivity is only on the symmetric part of the strain. And this is what creates difficulty in our analysis. Okay, so as I said in the title, they were nonlinear elastic models. So okay, here I'm starting from linear model, but to this energy, that is the elastic one, and that is what I want to see, I have to add the plastic energy in my analysis. And the reason somehow can be explained in the following way. So this energy is the total variation of mu serves only for compactness reasons. So it doesn't play any role on the effective energy that will be represented by the gamma limit. But the reason of putting this term here is the fact that if I have a measure for which the balls of radius epsilon cover the whole domain omega, then this set is empty. And so if I do not have this term, the energy is equal to 0. Since I want that my topological singularity pays something, it's completely somehow unphysical to have an energy that is 0 when I have too many dislocations. Okay? And so this kind of formulation appeared somehow in a paper 20 years ago by Cermelli and Leoni, where they studied the problem for a fixed family of dislocations. And then in Garroni, Leoni, Ponsiglione, when they start the limit as epsilon tends to 0 of this energy, when the dislocations are well separated. okay? So that they are at a distance larger and larger than epsilon. Okay, so this is my setting. And now let me do the first computation. That is to understand what is the energy cost of an isolated singularity. Okay, I want, as I told you, I wanted to do the gamma limit as epsilon goes to 0, and I want to observe these locations. So I need to know what is the regime I should look at. Okay, so this is a computation that you have seen, I think, a lot of times. So I assume that mu is just an isolated Dirac delta, that omega is a ball with radius capital R, and I assume that to have a field that is compatible with this measure here, mu. So beta is in L2 of the annulus, is scar-free, and satisfy the circulation condition. Okay, so if the energy were beta squared, okay, that is not the case, but the computation with beta squared is instructive, then I can use Fubini and say, okay, so the energy, this energy here is equal to the integral of the radii in the rho, and the integral of their circumferences of beta square, the H1. But I can estimate on this, of this circumference beta with its tangential part. And now, once I'm here, then I can use Jensen inequality to bring this square outside of the first integral. Okay, so this is beta tau squared, and I put the square outside up to pain 1 over rho that is in front of the integral. But then here, what I have is exactly the circulation here. So this quantity is constant, does not depend on the circumference, and is epsilon squared beta squared. And so the energy remains here as the integral between small rho and capital rho of 1, between small r and capital R of 1 over rho. And this is the logarithm of the quotient of the radii. So the energy in this case diverges logarithmically in the quotient of the radii. But now my energy is not beta squared, it's beta sim squared. Okay, so this is the only coercivity estimate that I have. And the only thing the basic thing that I do now is to estimate beta sim with beta squared. And this can be done with thanks to Korn inequality. Okay, so Korn inequality says that the L2 norm of beta sim squared can be bounded from below by the L2 norm of beta minus a certain skew symmetric measure squared. But when I have so this thing can be done, so this beta sim with beta squared, up to pain a constant that clearly diverges when the thickness of the annulus tends to 1. Okay, but in principle, the same estimate that I proved for beta squared holds true also for beta sim. And here the energy diverges as the logarithm of the quotient of the radii. So this is telling me that in order to see singularities, one should consider at least an energy regime that is log epsilon. So log epsilon, because in this case one has to put capital R, for instance, equal to 1 and small r equal to epsilon. And so this means that if I wanted to see effective singularities, this is the smallest energy regime. And this energy regime is compatible with having a finite number of isolated singularities. Okay, so this allows me to understand what is the regime I should consider, but these estimates here are not sharp at all. Okay, so this gives me just the regime. And okay, a way of understanding what is the minimal energy is to compute the minimum. Okay, so the first thing that one does in this case is that fixing a certain B, we can consider two annuli that are small r and capital R, and define the minimal energy over an annulus that have the right circulation condition. Okay, and we divide this energy by the logarithm of the quotient of the radii. We know that this term is finite also when somehow when the quotient of the radii tends to plus infinity. So the lim sup of this quantity is finite when the capital R over R tends to plus infinity. But what one can prove is that not only the lim sup is finite, but that this limit exists. Okay? And okay, for those of you who are familiar with the Ginzburg-Landau model, this is a B squared. Okay, so it's degree to the power 2. But here in the case of plane elasticity, is everything much more complicated because in the case of Ginzburg-Landau, the function that realizes this minimum is the gradient of x over modulus of x. And that is the solution of the problem on the wall R2. Whereas in this case of plane elasticity, this is not true for any annulus, but it's true only when the thickness of the annulus goes to plus infinity. Okay, and actually one has this fact that the minimal energy with a given Burgers vector is, so once the quotient of the radii goes to plus infinity, is given by the energy of the fundamental solution of the minimum problem on the wall R2. So, and this psi c goes like b squared. But then, as all the people working in Ginzburg-Landau know, and from what we have seen by the previous talk, the gamma limit is not d squared, but it's d. So one can go through another relaxation procedure that is represented by this phi c here, that is linear with respect to the length of b. So, and okay, if one wants, so a take-home message from this slide is the following. So if I have a singularity, I can, with a multiple weight, I can approximate it with singularity having somehow minimal weights that are approaching this the final singularity. Okay, so this identifies the gamma limit. And now what happens is that in the end, we are able to prove our gamma convergence result. Okay, that is made by two parts, the compactness and the proper gamma limit and gamma limit sup inequality. And so given a sequence of measure mu and beta as above, I assume that the energy is bounded by epsilon squared log epsilon. Then up to a subsequence, I have that the measure mu epsilon once scaled by epsilon converge in the flat norm to a sum of Dirac deltas. Okay, and the Dirac deltas have weights that are in this in the lattice lattices. And whereas for the gamma limit, the gamma limit is given by the somehow plane elasticity analog of the total variation of the measure that we have seen in the previous talks, and is represented by the sum over k of phi c of bk. Okay, a few comments, although we have already seen somehow these issues. So here the convergence is the flat convergence, that is the convergence in the dual of Lipschitz continuous functions with compact support, and is actually a strong convergence. And the point is the following, is that if I have a dipole that is represented by two singularities that somehow points in the opposite direction, so this, the total circulation around this dipole is equal to 0. So the minimum of the energy is bounded by a constant, okay? And so this means that the log epsilon regime I want to look at is compatible both with having a finite number of singularities in the limit, that is what I want to see, and both we have a log epsilon short dipoles, okay? That is something that I want to neglect. And so this is what the flat topology does. And this is somehow understandable if one see the definition, because it's the topology in the dual of Lipschitz continuous functions. And for Lipschitz continuous functions, once so I take phi of this dipole, I see the difference of the values of, not phi is not right, the right letter, but if I have a function f that is that acts over a dipole, so I have the difference of the values of f, and the difference of the values of f, if f is one Lipschitz continuous, is bounded by the L-infinity norm of the gradient of phi times the distance between the 2 points. So if the 2 points annihilates, then this flat norm tends to 0. Okay, and okay, I'm talking too much. So my idea was to present briefly what is the proof of this lower bound here, because this is somehow crucial. And this proof, okay, is based on the ball construction machinery that was introduced by Etienne Sandier, Bob Gerard. In so okay, we'll use the construction of Sandier, but it was used more or less, it appeared in the same year. So what is the idea? The idea is that if I have a set additive function, that is our energy, and if I have a logarithmic lower bound on annuli, then I'm able to construct a family a family of annuli in which I can somehow bound the energy in a very efficient way. So what I do, so I take somehow an artificial time t. I start from a certain family of a given family of balls, and then I multiply the radii of these balls in such a way that the quotient of the radii of the annuli that I'm constructing is constant for all the balls. Once I cannot do this procedure anymore because somehow I have two balls touching each other, then I create another family of balls that contain all these balls, and then I start once again with somehow this way of enlarging the balls in such a way that the quotient of the radii remains constant. Okay, so we have two warnings to look at when looking at this procedure. So first of all, the lower bound that we have does not allow to construct two tiny annuli. Because as I told you before, the Korn's constant somehow tends to 0 when the quotient of the radii tends to 1. So this means that I cannot construct these new balls in a continuous way, but at each time, discrete time, I have to multiply the radii by a fixed constancy that will go to 1 only at the end of my procedure. So the warning one is about Korn inequality that tells me that I cannot construct annuli with a thickness that is 1 plus epsilon. Because once I send epsilon to 0, the only estimate that I have is that the energy on this annulus is larger than 0. And the second thing that is somehow less important but plays a role is that our lower bound is non-optimal on any annulus. So the lower bound is optimal only when the radii are very, very thick. Okay? So what I do in order to avoid these procedures, we consider this construction that is discrete in time. We found a time in which we can reduce to a finite number of balls that have non-zero measure, okay? And then we have a lot of other balls that are with the zero measure, that are the balls of dipoles, and I fill these holes, somehow producing a small error in the energy. So the idea is that we use this ball construction for avoiding to look at the dipoles. And through this procedure, we can construct a new measure mu and a new field beta having the following properties. So this measure mu at times t epsilon is flat close to the original measure. Okay, because it's more or less, this measure is equal to this one plus dipoles. The new fields are compatible with the new measure. The new measure is bounded in total variation, so its weak star converges to a given measure. And the energy of the new measure and new field is a good lower bound up to small error of the initial energy. Okay, so all these bullets here are done only for avoiding to look at dipoles. Then we end up with this measure here, and then for this measure, we somehow reply to warning 2, then we are able to construct annuli that are thick enough, so have radii that are two different power epsilon, and on this annuli, we are able to bound from below the energy with the right stuff, that is this psi. And then we go through the relaxation procedure. Okay? So after killing you with this stuff, then I will present you what is the nonlinear model I want to look at. So, but keep in mind that some of the procedure also in the linear way is quite complicated, and the big problem is in the Gisborne-Landau problem is to avoid the dipoles. Once one has removed the dipoles, then everything is okay, more or less. And now let me look what is an idea of a nonlinear model for edge dislocation. So the closed section is once again the same. So it's the omega, the lattice spacing is epsilon. And now let me look at the dislocation measure. Okay, so in the linear model, the weights were given and belong to the same lattice spacing. Since here I'm in nonlinear setting, then in principle, I could have different rotations. Okay, so the weights of the dislocations can lie on different rotation of the same lattice. So this dislocation measure is represented by this sum of Dirac deltas, where the weights now are in principle in different lattices that are obtained, that are rotated one respect to the other one. Now I adopt the same idea as before. So the strains behave locally, so as the gradient of the deformation. But now the deformation, I've not linearized. So in principle, I have that the gradient of the deformation is the rotation of the identity plus a certain small gradient of the u, where u represents the displacement. Okay, and now the strains that are beta that are compatible with mu are given by those matrix fields, which are still curve-free, because far from the dislocation, don't see anything, that still satisfy the circulation condition here, plus a further condition that was not present in the linear model, that is the following. So if the Burgers vector lies in a rotation of a certain rotation of the lattice, then I want to see that the closest rotation to B is exactly the one observed by the Burgers vector. No, because otherwise I obtain two variables that are completely decoupled. So I have that beta linearizes around a certain rotation, and the Burgers vector so belongs to another rotation of the lattice spacing. And in order to see that condition that beta is close to the right rotation, so we decide to put an average condition of this type, namely that the average of beta on an annulus with the radii epsilon to the power gamma, where gamma is larger than 1, is smaller than 1, is equal to Rn. So up to the rotations that leave the invariant the lattice. Okay, so in order to put this condition, we have to assume that the balls that are centered at the singularities with radii epsilon to the power gamma are pairwise disjoint and contained in omega. So we have a well separation assumption on the singularities. So this is the model for what concerns the definition of dislocation and of the admissible strains. And then we have to define, to introduce the energy. And the energy is the standard nonlinear energy. So it satisfies all the assumptions in this sense. So if you don't want to read this slide is a square distance of the strain field from the rotation. Okay, otherwise it's something that behaves exactly in that way. So it's a potential that is 0 over the rotation. It's a frame indifference. This means that some of the energy that I compute does not depend on the rotation of the axis. Okay, this means that this invariant with respect to the symmetry of the lattices is controlled from above and from below, but square distance of the rotation, and is a C2 in a neighborhood of the rotations. And this is something that guarantees me that I can linearize it. And actually define the linear tensor associated to this nonlinear density in this way. Okay, so as I told you before, so the condition that the energy, linearized energy, depends on the symmetric part of the strain somehow depends on this stuff. If one linearizes this condition, then one ends up with something that is coercive only in the symmetric part of the strain. Okay, formulation of this type already appeared in this paper where the problem what was observed by another point of view, and I will explain you in a while the way. What is the formulation in this paper? And okay, so this is now that I have the energy, I can do the gamma convergence analysis and the compactness problem. And this is something that we proved in 2 years ago, but it appeared this year. Okay, so where we work in the same dilute regime log epsilon, and if the nonlinear energy satisfies this bound, then we are able to find a sequence of rotations that converge to a finite rotation, and measure mu, that is a sum of Dirac deltas whose weights lie in this rotation R of the lattice, a field beta that is curve-free, such that up to a subsequence, okay, the rotations converge to a rotation, this beta epsilon, once I subtract the rotational epsilon and I scale by this term here weakly converge to this field beta in L2, and such that the measures mu epsilon over epsilon weak star converges to the measure mu. Okay, so few words. So this condition one didn't appear in the linear case, and actually, so this is something that is not very relevant in our analysis, because as you see, mu epsilon is scaled by epsilon and beta epsilon is scaled by something. So the two variables that at the beginning, when epsilon is positive, are coupled, because Carlo beta epsilon is equal to mu epsilon. In the limit, we are completely decoupled. And okay, and the other thing that I want to stress is that in principle, we started from measure mu epsilon whose Burger's vector could lie on different rotations of the lattice spacing of the lattice, but within this regime that is log epsilon, somehow all these rotations align in the same rotation. Okay, and this is due to the fact that we have a regime that is smaller and smaller than 1 over epsilon. And okay, and now the third thing that I want to point out is that I have a weak star convergence. Okay, instead, so I have a stronger convergence with respect to the previous one. Okay, and now the proof of this fact works somehow is easier with respect to the other fact. So first of all, we need a control of the energy on the annuli. Okay, as we had in the previous case. So we need the nonlinear analog of coarse inequality, and this is the Friese-James-Müller rigidity estimate that says the following. So that if I have an energy, the nonlinear energy, square distance from the rotation, okay, this the energy governed by this potential can be bounded from below by the distance of just one constant rotation. Okay, up to paying something that is a constant that depends, in case of annuli, from the quotient of the radii, and this constant clearly tends to 0 when the quotient of the radii goes to 1. Okay, but then if one has this estimate here, then actually arguing as before using what was Fubini and Jensen inequality, one ends up with the same estimate, logarithmic lower bound. Okay, so Friese-James-Müller proved this estimate for gradients, and then Scardiazzi-Pieri specified it to the case of fields that are curve-free and satisfy a circulation condition. And now what happens is that in view of the well separation assumption, I have that these annuli that have a larger radius equal to epsilon to the power gamma are disjoint. So the total energy is an upper bound for the sum of the energies computed in the annuli with radii epsilon to the power gamma, and then using this lower bound, specializing it to the case small r equal to epsilon, capital R equal to epsilon to the power gamma, we end up with this estimate here. And as you see, in the left-hand side and the right-hand side, you still have epsilon squared log epsilon that cancel each other. And now we end up with the fact that the total variation of the measure, when scaled by epsilon, is finite. So in this case, I have weak star convergence because I'm starting from well-separated dislocation. Okay? And now this is something that makes life easier and easier because somehow, as you see, also in the lower bound, I have not to do all the steps that I did before in the linear case. And the last thing about this is that, okay, I'm finishing in a while, and is that there exists a constant for which I have a global rigidity estimate, okay? So I have a rotation that is close to a beta epsilon, and this somehow explains point one, and the fact that all the Burger's vector align in the same with the same rotation. Okay, I try to finish in time. Finally, we have the gamma convergence result that says that the gamma limit, okay, in this nonlinear case, is given by the gamma limit. Okay, let me look first at the measure. That the gamma limit is the same as that we have computed for the linear case. Okay, so the fact that so we start from a nonlinear energy, but when we are somehow close enough to a singularity, we are linearizing around, so the minimal energy is the one obtained by linearizing along one rotation. And this term here does not matter at all. So this is something that comes from the far field bit epsilon. So don't look at this one. Okay, and the proof of this fact, so we can skip everything that was in the bullets below. We have to look just what happens in the last bullet. So we can construct annuli that are thick enough. And in this annuli, we have to perform linearization in order to end up with this gamma limit. Okay, I'm almost, no, I'm not finished. Okay, so I have 4 slides in which I say that the same thing can be done in the discrete lattice, but I will use the last 2 minutes that I don't have in order to tell you that what I said until now, it's not really right. So, not from the mathematics, I hope, but from a modeling point of view. And the picture is the following. So this, the first picture I have was this one with this orange thing that was below. And now let me perturb in an elastic way this picture. And let me do what I did at the slide number 3. So I take the Burger circuit and I try to replicate the Burger circuit. I said, no, this is not closed. I have to come back by a vector that is a lattice vector. But actually, if I perturb this thing here in an elastic way by very, very small displacement, what happens is that this is not a lattice vector, okay? And so is everything I say wrong? Not really. So we see that this red vector is almost horizontal. Okay, it's not horizontal, but it's almost horizontal. And maybe the right way of looking at this location in a linear setting is the following. So instead of drawing the Burger circuit in the reference configuration and then to replicate it in the deformer one, we should go in the opposite direction. So I consider a lattice that is closed in the reference a circuit that is closed in the reference configuration. I go back constructing a map that somehow goes in the reference configuration. This is ideal. So it's something that I should construct. And then here, all the vectors that I see are in the lattice, in the right lattice. Okay? And so this is, just to say, this is something that one can do. So in this way, the admissible strains are the gradient of the inverse deformation. Okay, and with this way, see, I can always choose the same lattice. Okay, so I don't need with this kind of stuff to put any condition on the average. I can consider that these locations so can satisfy mild separation, or I can consider the energy as before with the total variation. And with this kind, in this kind of model, although it's non-linear, using the machinery of the Ball construction that somehow it uses only the fact that I have a set additive function that is the energy, that is additive, and that satisfies the logarithmic lower bound, as I shown you before, I can prove exactly the same stuff. And what I end up is the same gamma limit with the rotation. That is telling me that although I've chosen a reference configuration that was not the right one, however, I'm able to do all the computations. Okay? And so this can be done, and we have studied everything in the log epsilon. Okay, just one thing I want to say because I skipped this part. So this kind of analysis works since I work in the semi-discrete model, so my energy is continuous. But if I have a discrete energy, it's much more comfortable with working with an energy that is defined on lattices. So in this case, I should reconstruct the right lattice at every step, and this is not simple. Okay, because I cannot define this gradient in an easy way. And we have done everything in the log epsilon regime. And this kind of procedure of the Bose construction is somehow robust enough to be extended to multi-well energy densities. And the next step we want to try this is the log epsilon squared regime. That is called the critical regime, because in this case, I have convergence of both the measure and of the fields. And these that are related also when epsilon goes to 0. And in this case, the effective energy is not only this somehow the total variation of the measure, but they have an elastic part that looks at interaction of the particles. And I think that are enough, and I stop here. Thanks.
Thank you, Lucia, for your very nice presentation. Are there questions from the audience?
Thank you very much, Lucia, for this very nice talk. I was wondering, in the dilute regime, so basically all you talked about, could you go also further in the gamma convergence expansion, like do renormalized energies or stuff like that?
Okay,
the non-linear case?
Not even in the linear.
Oh, not even there.
Because the fact that we have to construct two thick cannuli is something that we are not able at the present to overcome. So for the log epsilon squared regime, in the linear case, it has been done by Janusz Ginster in his PhD thesis. I don't know if I'm saying the right thing, but in log epsilon regime, since you scale the energy by log, so also in the log epsilon squared, since you scale the energy, you can kill the errors. Whereas in the log epsilon regime, since you don't scale, you just renormalize, then at the present we are not. So we have stopped at a lot of time, but
thank you.
So we don't know. Yeah.
Yeah, I want to ask, what do you mean by multi-well energy density?
So yeah, I didn't explain. So not only square distance from the rotation, but also square distance from union of SO2 times a certain rotation. So R1 of SO2 union R2 of SO2 and so forth. So that should not be rank 1 connected. No, not R1. So A1 of SO1, 2, and so
okay.
It's better if I write it.
Yeah, so it would be like the generalization of Montet von Schachtingen and things like that. No?
Yeah, so it's a finite union. Okay.
All right.
But yeah, just yes, finite case. And because in this case, one can do linearization and one can prove the Friese-James-Müller estimate. Where these things are not rank 1 connected, because otherwise it's more or less impossible.
Okay, thank you.
Are there any other questions? Does not seem the case. So let's thank Lucia and all the speakers of this morning session again.
The next speaker is Nicola Fusco from the University of Naples, and he will talk about consistency for the surface diffusion flow in 3 dimensions.
Okay, first of all, let me thank the organizers for inviting me, and let me also apologize because my talk is not in the mainstream of this conference, but on the related topics. But nevertheless, I hope it could be of interest for some of you. And more specifically, I will discuss some recent results obtained in collaboration with Marco Cicalese, Vesa Yulin, who are also here, and Andrea Kubin, concerning the surface diffusion equation, which is the following. Here we have a family of evolving sets E sub t, evolving in time, with the following law. The normal velocity at the boundary of at each time of the evolving set is required to be up to a constant, so it's proportional to the Laplace-Beltrami operator on the boundary of the set. Laplace-Beltrami operator applied to the mean curvature. I call it mean curvature, indeed it's the sum of the principal curvatures of the sets. And this is the Laplacian on the boundary of the set. This equation was proposed in a series of papers by Mullins to model the evolution of interfaces controlled by mass diffusion within the surface, and as several applications which were exploited by Mullins, David Gertin, and other authors, several applications to phase transition, epitaxial deposition, grain growth. It's
not so well known, especially if you compare this equation to the much more popular mean curvature equation, which is the first one here. The normal velocity equals to minus the mean curvature. But in a way, they are similar in the sense that they are both a gradient flow of the perimeter. Okay, this is a technical fact for mathematicians only, but it can be formally proved that while the mean curvature equation is the L2 gradient flow of the perimeter, in some precise sense, the surface diffusion is the h to the minus 1 gradient flow of the perimeter. And as you can see, is a fourth order parabolic equation. So compared to the first one, which is a second order parabolic equation, it has a completely different behavior, but quite interesting, especially in view of physical application that I mentioned before. First of all, surface diffusion is volume preserving. If you take the derivative of the volume, for physicists, this is the way we measure indicate the volume of a set. This is the integral over the boundary of the normal velocity. This again stands for the measure on the boundary, which by the equation is given by this Laplacian, and the integral of this Laplacian is 0. So the equation is volume preserving. Second feature, this equation, while is volume preserving, decreases the perimeter because again, now you differentiate the surface area at each time. Again, this is given by an integral on the boundary, this time normal velocity times the mean curvature, but use the equation. This is the product of the mean curvature times the Laplacian, integrate by parts, and you get minus the gradient squared of the mean curvature, which is non-negative. So it decreases the perimeter, and differently from the mean curvature equation, surface diffusion does not preserve convexity. If you want to make a mental picture of how this equation acts on a set, it makes oscillate the boundary in such a way to keep the volume but adjust the shape of the boundary so that the perimeter decreases. While mean curvature equation shrinks your initial set and makes it possibly as convex as possible. If you start with a convex set, you will remain actually convex and eventually converge to a ball. As I said, this is a fourth order equation, so there is no maximum principle, no comparison principle, and this makes the analysis from the mathematical point of view quite unpleasant. And in fact, another feature is that even in this is yet another difference with mean curvature equation, singularities may appear even in 2 dimensions. If you have a curve of this form in 2D, there is a calculation contained in a paper by Giga and Ito, going back to 1998, that showed that if the neck is sufficiently small, then you develop a singularity in finite time. It's again a difference with the mean curvature equation that instead does not develop singularities in 2D. So what is known? There is a general and very nice result due to Escher, Meyer, and Simonet, which proved the existence for small times, even starting with a C2 alpha initial set. And they show that if you write the boundary of the evolving set as a normal graph over the boundary of the initial set. So you have your initial set, and as the evolution goes on, you are able, for small time, to write the boundary of the evolving set as a graph, well, these functions are in fact instantaneously smooth after the time 0, and in fact they are taking continuously the initial datum with values in situ alpha. So we have existence. We have also asymptotic behavior of these of the solution of this equation, because Steele, Escher, Meyer, and Simonet, they proved that if you start sufficiently close to a ball, remember the equation wants to decreases the perimeter. So the idea is that if you start very close to a ball, the best thing you can do is converge to a ball. And this is in fact what they prove. Convergence to a ball with a slightly shifted turn. A similar result concerning the asymptotic behavior can be proved under periodicity condition. This was proved by Acerbi, Vesa, Yulin, Morini, and myself in 2 and 3D, and later on by Antonia Diana, Mantegazza, and myself, and with a different proof by De Gennaro, Diana, and the 2 Kubin brothers 1 year after. And again, well, if you are in the periodic setting, you have a much higher variety of critical points of the perimeter. And what is proved in this paper is, again, that if you start sufficiently close to a stable critical point for the perimeter in the periodic setting, the evolution will go on for an infinite time and will converge, suitably converge to this object. So the equation likes critical points of the perimeter. Okay, this is more or less what is known, and the aim of this talk is to discuss a problem which is not just a mathematical curiosity, but as useful application from a computational point of view. That is, we would like to understand if it is possible to approximate this equation with a time with a discrete scheme in time. Well, this kind of question is very popular in this setting, and let me remind you the case of the for the non-expert in the audience, the case of the mean curvature flow, where this discrete in time approximation was first proposed by Allen-Cahn, Taylor, and Wang, which in fact proposed the following scheme. You fix a time step, start from your initial data, and at each time you solve this minimum problem. You minimize the perimeter, the measure of the boundary of a set, plus a dissipation term, which is given integrating the symmetric difference of your set with the previous one that you constructed. You integrate the distance of your point from the set and divide by the time step. So you start doing this at time 0, get the first step, and then you repeat the procedure. And okay, in this way, you have a discrete sequence of sets that you can imagine to be a continuous just by trivial interpolation. And the key point is that, okay, you have to take it in mind that this kind of approximation through a minimization problem is much more convenient if you want to make numerical simulations. That is the reason why you like this kind of approximation. Then what it was proven by Allen-Cahn, Taylor, and Wang, and also Lukaus, Sturzenegger, is that this sequence of set converge in a proper sense, which it's written here and which may appear weak in the sense that the symmetric difference goes to 0, and the difference between two sets at different times is controlled by this elder continuity modulus. Anyway, in this sense, they converge to a family of set, and this is the important point, the limit family of set E sub t is in fact coincide in fact with the unique smooth solution of the mean curvature equation as long this smooth solution exists. So in a way, this is also a trick to give a meaning, and there is also a lot of literature on this aspect, meaning to the equation beyond the existence time of smooth solution. But as long as you remain in a time where smooth solution exists, this guy converge to the right solution, which is unique. As I said, the mean curvature equation does not preserve the volume. So from point of view of applications, people like often to work with the volume preserving mean curvature flow, that is the same equation to which you subtract the mean. This symbol stands for the mean, the average of the mean curvature over the boundary. So in this way, you get a volume preserving flow. And this has been studied more recently by Mugnai, Seis, and Spadaro. And the problem of while the problem of consistency, that in this case is much harder, was recently given by Vesa-Yulin and Ninikowski. Okay. As I said, the mean curvature equation, let me write the two guys. This is the mean curvature equation. This is the surface diffusion, okay, in which I have normalized the constant and taken to be equal to 1. As I said, the mean curvature equation is the L2 flow, gradient flow of the perimeter. And in fact, this dissipation term contains a sort of L2 distance between the set that you previously constructed and the new one, because why this integral is the square of the L2 distance. Because assume again, for convenience, that you have a set E and a set F whose boundary is again represented by as a normal graph with respect to the boundary of the set E. Well, this integral is up to a constant from below and from above, equivalent to the integral over the boundary of the square of the function psi. So it's the L2 norm of this function. On the other hand, I say that this equation is the h to the minus 1 flow. So one has to, if you want to reproduce this sort of scheme for the surface diffusion equation, you have first to imagine what is the counterpart, the h to the minus 1 counterpart of the L2 distance between two sets. And this is not an easy task at all. And but the scheme in this direction was proposed by Kahn and Taylor. And the scheme is similar to the previous one, except that now you have an h to the minus 1 distance between the two sets. squared again and divided by the step time. This is the definition, the formal definition of this h⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ integrate against, okay, this guy is the difference of the two characteristic functions, is the natural object if you want to measure some distance between the two sets, but then you have to integrate this guy against a function evaluated in the projection on the boundary of a generic point in Rn, and this function is a function in fact defined only on the boundary. So each time you have a function on the boundary, you look at this, extend if you want this function on the whole Rn in this way, and you want to maximize this integral among all functions on the boundary whose gradient as L2 norm less than or equal than 1. So why this is, let me explain why this is the right counterpart of the L2 distance. First of all, because it does what we want. Remember, we want the equation is volume preserving, so if this scheme should converge, it should remember that we want a volume preserving evolution. And in fact, if the two sets have different volumes, this supremum is trivially equal to plus infinity. So if you minimize this problem, you are forced to choose a set which has the same volume. And the reason is very simple, because if you take a constant here, and this integral is just difference of the two volumes, and then you let the constant go to infinity, and so that distance is infinity. Again, good news, because put yourself in the very simple situation in which the boundary of your set E is flat, or you make a variation on the flat part of the boundary. Again, the variation given by the graph over the boundary of some function psi. Then small calculation shows you that the square of the distance, of that distance, is the square of the h to the minus 1 norm of the function psi, which in turn is what? Is the integral of the gradient of the solution of the Laplace-Beltrami equation over the boundary minus Laplacian u equal to psi. This is the way the h to the minus 1 norm is usually defined in the flat case. So this is good news. So you take this equation on the boundary of E and you impose the function u as a zero average, you get a unique solution, and that quantity above gives you the integral of the gradient u squared. Okay, if your boundary is not flat, of course, if you want to calculate that distance, the curvatures of the boundary must come into play. But again, what you get is very reasonable. Now assume, as before, that you have a set E and another set F whose boundary is given by the normal graph of the function psi on the boundary of E. And in this case, you can prove that the square, you can calculate the supremum, and the square is given by the h to the minus 1 norm of something which I called psi, which again is the integral of the square of the gradient of the solution of the Laplace-Beltrami equation on the boundary, with the right-hand side given by the function psi, plus this is in 3 dimensions. Otherwise, you get all the homogeneous function of the principal curvatures with appropriate coefficient. Here you have 1/2 of the mean curvature psi square, 1/3 of the Gaussian curvature to psi cubed. But this is unavoidable. So up to this, let's say, lower order terms because you have to imagine that if your time step is very small, function size very small. So what really counts is this. This is more or less what you have as in the flat case. The distance, this is next slide. Next slide will answer your question. Bad news, the distance is not symmetric. Well, not even the previous one was symmetric, but the previous one is controlled by something which is symmetric from above and from below. But even worse, the scheme proposed by Taylor and Kahn and Taylor was to minimize this problem. And up to now, it's not clear whether, in general, this problem has a minimizer or not, because this distance is too weak. It seems too weak. We don't know. But it seems too weak to allow you to control loss of mass at infinity. You don't know what happens if a possibly minimizing set go to infinity. So you say, okay, this is the end of the story because you don't know how to minimize, but we will survive in a way or not. So we don't know this, and this is not symmetric, but there are another bad news. This is a very strange distance because in this very simple picture, your set is this rectangle. You make a hole in the rectangle, move up the hole, you get another set with the same area, and the distance between the two sets, that distance is now 0. And again, this is very bad, but not so bad from the point of view of this minimum problem, because the distance is 0, but the perimeters are different. So at least the minimum problem, see the differences between the two sets. Okay, so let me go back to the conjecture by Kahn and Taylor. So again, the idea is that you start with your initial datum at time 0, and given a time step, you consider the minimizer, which if they exist, there is no reason why to expect they are unique. But let's say you take a minimizer of this problem time by time and construct a sequence of set that you want that converge in some sense to a smooth solution of the surface diffusion equation. Okay. As far as I know, after this paper by Kahn and Taylor, the only attempt of attacking this problem is contained in a PhD thesis of a former student of Gene Taylor, Chung, that simplified the problem by simplifying the distance, by replacing this distance with a simpler one in which, first of all, you have a function defined in the whole Rn, not this strange composition of the projection with a function defined on the boundary. A Lipschitz function with a given bound on the Lipschitz norm, and the L2 norm of the gradient bounded by 1. Using this distance, he was able to show that minimizer of this problem exists, that they converge as h as the time step go to 0, and even if these constant blow up, but they have to blow up with a certain rate, but they converge to something that we don't know whether or not is a solution of surface diffusion. So it's, let me say, not very useful from this point of view, if you want to reconstruct the solutions. So there is no proof, not even a formal, even if you try to make a formal proof, is not clear if this the set constructed by using this distance, by putting this distance in the dissipation term, converges or not to the surface diffusion. Okay, so first of all, as I said, a major problem was that we don't know if this minimum problem exists as a solution or not. So to overcome this difficulty, we decided to change a little bit the scheme by imposing that the set F, for which you want to minimize this quantity, is as the boundary contained in a tubular neighborhood of the original one. So in order to avoid this possible escape to infinity. So what we do, we fix a small delta. Okay, we fix the usual. First of all, here we make no savings on the regularity. So start with a C5, but who cares? From the physical point of view, you may imagine to start with whatever smooth set you want. And let me say also something. All the results I will present are 3D only. Well, 3D, which means also two-dimensional. And there are several reasons for which we are forced to consider only a three-dimensional case. And one of these reasons will appear if I have time in a few minutes. Okay, so we do the following. Fix the time step H, fix. So you have your previous set here. Let's say EI minus 1. From now on, I will drop the dependence on H and delta, and we minimize by forcing the new sets to be contained in this tubular neighborhood. So to be not too far. And then the first theorem we are able to prove is the following. Again, assume your initial data is sufficiently smooth. Then there exists a delta zero. Delta zero is the width of this tubular neighborhood in which we consider the minimum problem, such that for any delta less than delta zero, if the time step is sufficiently small, the solution at each time step of this minimum problem is a normal graph over the initial datum E0, a normal graph of a function which has 4 derivatives, which are uniformly bounded. This function, moreover, converge in this sense to a function of x and time, which describes in turn the boundary of a family of set, and this set are the unique smooth solution of the surface diffusion for a small time. So, as you can see, we introduced this parameter delta for technical reasons because we didn't know how to solve the minimum problem, but luckily this parameter plays no role. You can fix whatever small you want. It doesn't matter because if the time step is sufficiently small, your solutions are smooth in this sense, and they converge no matter which delta you have chosen to the right guy. Just in H, for every delta, this converging. L infinity in time with values in C to alpha to this. But there exists a delta zero and the time T0. So you have convergent to smooth solutions in small time. While we aim to do better, to prove consistency. And in fact, this can also be done. Well, first of all, this theorem in particular gives an independent proof of existence for small times, because we do not require this information in order to prove the theorem. And but in fact, we have consistency, which means that assume you know for some reason that the smooth solution exists for a larger time. Then the previous scheme, in fact, converge if delta, if you choose delta sufficiently small, converge to the right guys for all t strictly smaller than the maximal time of existence for the smooth solution. So this tells you that things work well. Okay, now I have 4 minutes. I wanted to, not to give an idea of the global proof, which is too heavy, but at least to give a flavor of the first part of the proof, because this h to the minus 1 distance has no much geometric meaning, and so to retrieve the first initial information in order certain technical machinery work was the major difficulty in this problem. In particular, what was the major difficulty in this problem? Well, in the end, you want that the distance, possibly a reasonable distance like the L2 distance between one set and another in the discrete in time approximation, grows like the time. Otherwise, you are lost. And this is not this is immediate, more or less immediate, with the L2 scheme that you use for mean curvature flow, but it's not at all clear if you use the h to the minus 1. It's not even clear that the h to the minus 1 distance grows in this way. And you have another difficulty. To prove the theorem, you have to write down the Euler-Lagrange equation at a certain point and play with that. But you have a constraint here. So in order to write the Euler-Lagrange equation, you have to show that at least when the time step is sufficiently small, you don't hit your set dot hit the boundary of the neighbor, so that you can write, you can say, okay, my minimizer is well inside, I can write the Euler-Lagrange equation. So you need to show that here I say there is an h, which I'm not writing to simplify the notation, that for h sufficiently small, the L infinity distance between the minimizer at the previous step and the minimizer at the next step is much smaller than delta. These are the two main challenges. And let me, and of course, this will imply that you satisfy the Euler-Lagrange equation. And maybe, do I have a few minutes? Okay. Let me give you an idea of how we solve this problem. The key observation was a factor that is well known if you have a set E which satisfies the uniform bond condition with a certain radius. So a set E for which you may construct at any point on the boundary an interior and exterior ball of radius R0. These sets are quasi-minimizers of the perimeter, in the sense that if you take another set and compare the two perimeters, the perimeter of this set satisfying this uniform ball condition is smaller than or equal up to a volume error term, which depends on the radius of the of the uniform ball that you may construct inside and outside. Okay, so first step in the proof was to show that if you have a set which satisfies uniform ball condition with a radius R0, and for which the second derivative of the mean curvature are bounded, you have a similar property for not the L1 distance between the two sets, but the h to the -1 distance between the two sets. Okay, you say, but you are assuming a lot. Yes, I am assuming a lot, but I'm hoping that since I start with a very smooth guy, C5, during the evolution, I can keep the control at each step on this. If I can do so, this is a very nice information, because this nice information immediately leads to tell you that the h to the -1 distance between one set and the next one grows linearly. And the proof is trivial, because if EI is the minimizer of this problem at the next time, by definition, this energy is smaller than the same energy in the previous set, where this distance is 0, then this inequality satisfied by the previous set tells you that this perimeter is smaller than the perimeter of EI plus a constant times this distance, and the conclusion is that the two distances differ by h. This was a crucial point, because from this crucial point, we were able to, okay, let me skip the slide. Let me conclude from this crucial property. We were able to show that by using the regularity theory for minimal surfaces of de Giorgi, in this case applies to quasi-minimizer, to prove that if EI -1 satisfies this bound, less than a constant, then the set EI, which is close in this distance, is in fact EI is close in C1 to EI -1 by a constant controlled by a constant sigma. So this, together with the minimality, implies closeness with a constant which does not depend on h and is not going to 0, at least for the moment, as h goes to 0. But once you have closeness in C1 and closeness by h in this norm, by interpolation, you conclude that the distance in L-infinity between the new set and the previous one is controlled by a constant times a power of h. And if h is small, this is smaller than delta. Then you can finally write the Euler-Lagrange equation, and this is the beginning of a terrible technical story that I will not tell you. And thank you for your attention.
For the nice talk. Are there any questions, Giuseppe?
So the surface diffusion flow keeps the volume constant and decreases the perimeter. So is it reasonable to expect that the perimeter decreases continuously, or the perimeter could have jumps during the evolution?
In this case, in fact, you get that perimeter decreases continuously, because once you have a smooth evolution, the derivative of the perimeter, you calculate the derivative of the perimeter. This is given by an integral, and this integral is a continuous function in time. So it decreases.
This occurs up to the point where the flow exists.
Up to the point where the flow exists. In fact, we are not able to show that this discrete scheme converges for all times or beyond the time where the maximal solution exists. So this is only telling you that as long as the maximal solution, the classical smooth solution exists, this scheme works as an approximation, as a discrete approximation of the flow.
Okay, another question.
This might be very naive. I don't know much about surface diffusion. Is the story easier for curves in R2 or?
Yes. It's easier. The first part, the control of the h to the -1 norm, and then the conclusion that you are closing L infinity is much simpler. Is much simpler in 2D. Because certain inequalities concerning the perimeter are trivial in a sense. But then I would say the PD part, the PD estimates, okay, in 3D are much more technical, but more or less the same difficulty. But the starting point, in fact, I have to say that we started first with a proof in 2D, and then later on with the proof in 3D. And for the proof in 3D, this initial part was the main challenge. In 2D, the geometry is so simple that this is not too difficult. This kind of estimate is not too difficult. And this is also the reason why we are stuck in 3D, because we need to use the regularity, and we get regularity in C1, and then by interpolation, this estimate only in 3D. In higher dimension, we don't have enough information to deduce C1 closeness.
And you can't prove convergence of the scheme in 2D past the singularity?
I don't know. We did not think of this. We did not think of this. Maybe it's more feasible. Maybe, but I don't want to say something that we did not think about.
Okay, so we thank Nicola again. Okay, so the next speaker is Etienne Sandier, and he will talk about sorry? Perfect, because the title, Minimizing Entire Solution for the Vector Valued Allen-Cahn Equation.
Yes, this is it.
Thanks.
Thank you very much. And thank you to the organizers for this very nice conference in Pisa. I learned lots of things in the conference. So what I'm going to talk about is joint work with Peter Sternberg and with Lia Bronsard. So there is a paper that we completed with Peter a couple of years ago, and one that we just completed with Peter and Lia last month. So I'm going to talk about the Allen-Cahn equation, well, more precisely the vector Allen-Cahn equation. So I'm going to write the functional here. So it's defined like this. So it's a very mathematical talk, I'm sorry. But yeah, why sorry? That's true. Let's be proud. And Yeah, so you have a gradient term, and then you have a potential term, which is like this. Yeah, sure. Okay, so you're integrating on a domain omega, okay, which could be the whole space, but well, in fact, for the energy to be finite, in interesting situations, you would have a bounded omega. And the Euler-Lagrange equation for this would be just Laplacian of u is equal to the gradient of w evaluated at u. So you have several cases. So you have the scalar equation, the vector equation. So in the scalar case, you would have a u. So generally, you would have u, which goes from omega to some r to the k, okay? And then w would be a function from r to the k to the real numbers, well, the positive real numbers in my case. And in fact, so the scalar case would be k is equal to 1, and the non-scalar case, k different from 1. And what is known since the pioneering work of Modica and Mortola is that, in fact, you have a deep connection between this equation and geometric objects. So this is expressed, sorry to physicists again, by gamma convergence. I'm sure you are very used to this word by now. And so for the scalar case, so let's say you have, so I'm going to describe the gamma limit. So let's say first in the scalar case, but it could also be the vector valued case, or k greater than or equal to 2, but 2 wells. So what do I mean by that? Is that so your potential W, so I will draw the function W is a function with 2 wells. Okay, so P1 and P2. So it could be scalar valued or vector valued. U could be, K could be equal to 1 or greater than 1, but in any way, W will have 2 wells, so it increases nicely at infinity, it is smooth, and the 2 wells are 2 minima, which are non-degenerate, so where the second derivative is positive or positive definite in the vector case. So, so the link between Allen-Cahn and geometric object is with minimal surfaces and perimeter, and it comes from scaling. So if you have, say, a very large omega, you can look at it from a distance, and then the interfaces will become just very thin, and they will become sharp, and you will get minimal surfaces. So that's exactly, so the way stated is that you make a rescaled version of the functional, E epsilon, which would be, let's say, 1/2 integral of grad u squared, but now you will have 1 over epsilon squared times the integral of w of u, because the two terms do not scale in the same way. And you're going to show that, okay, so the exponents, so you have to check the exponents, but that epsilon, E epsilon, so it gamma converges to the perimeter, okay, to a certain constant, C times the perimeter. Okay, so I'm not going to state very precisely what this means. In particular, if you minimize these functionals, then you have to put some boundary conditions or some constraint for the minimizer not to be trivial. Otherwise, the minimizing U would just be the constant P1 or the constant P2. But if you put a suitable constraints, you can have some different minimizers. So this gamma convergence tells you that, okay, if you take minimizers U epsilon, so you have different choice of constraints, but I'm not going into the details. So they will converge to, as epsilon goes to 0, to a certain U naught, which is in BV of omega with values in the set P1, P2. Okay, so these are minimizers, and U0 minimizes the perimeter, so certain constant, which depends on W, times the perimeter of the set where U0 perimeter in omega, where the set of U0 is equal to P1. So I repeat again, of course, you have to put some constraints for the minimization, and they will translate into a constraint for the map U0. Okay? And what is the constant you find here? So it's very intuitive. So CW is the energy you need to transition from P1 to P2. So you can, I will use a notation D12 in the following. So it's sort of distance between P1 and P2. And it's defined as the infimum of the energy of a one-dimensional transition. So 1/2 of the integral of gamma prime squared plus the integral, so this is from -infinity to +infinity, -infinity to +infinity of W of gamma of t dt. So gamma is a curve in R to the k. So here it's just a function. And the infimum is for gammas which join P1 to P2. So gamma of -infinity is P1, and gamma of +infinity is equal to P2. Okay, so the existence of such a gamma, of a minimizer, is in itself an interesting question, for which you have recent papers on this subject. And but okay, so anyway, this infimum exists, even if it's not achieved. But in the situation I described, it is achieved. And so this, so CW or D12 is achieved in this situation by a certain function that I will call zeta12. Okay. And which people in a dynamical system, so they would call that a heteroclinic connection between P1 and P2. Okay, and so now to explain the gamma convergence statement, so what happens is you have omega, okay? So when epsilon goes to 0, this is very highly penalized. So U wants to be equal to P1 or P2. But because you have put some constraints, it cannot do so. So it has to be equal to P1 somewhere, maybe because you impose the volume fraction or something like that, or because you impose some boundary conditions. And it has to be equal to P2 somewhere else. And the energy to leading order is the surface of this interface, okay, times the transition energy. So here you see a minimizer, if you want, would be something which transitions along this curve here, because I'm in 2D, and here you would have a zeta 1 2, if you want, in this normal direction. Okay, so this picture is due to Modica and Mortola in the 70s. So they called that an example of gamma convergence. And you also have, this is proved in the scalar case. And it was proved by Peter Sundberg at the beginning of the 80s, I think, in the vector case. Okay, so in the vector case, you can generalize this to a situation with several wells. So that's the main distinction with the scalar case. Although, of course, in the scalar case, you could have multiple wells also. You could have these. But we will see that this is very special. So for the moment, I don't want to consider this, although I will later on. But if K is greater than or equal to 2, then you can have multiple wells. So you can have a potential which looks like this, for instance. Okay, so this would be the graph of W, and you would have several wells here, P1, P2, P3. I'm not sure my drawing is excellent, but well, maybe you get the picture. Do you? Yes? Okay. And so you have several wells. And so you can, in this case, so this case was considered, so the gamma convergence in this case was established by Sistobaldo and independently by Fonseca, Irene Fonseca, and Luc Tartar in the 90, I think, 89, 90. And so you can define in a similar way D12, Dij, if you want. You have a certain number of wells. But to have the gamma convergence result, you need to assume something more, that the Dij's satisfy a strict triangle inequality. So that Dij plus Djk plus Dki, excuse me, is strictly greater than Dik. Okay, for any ijk, a distinct ijk. So you have to assume this. But if this is true, then you also have a gamma convergence result, meaning that a minimizer, U epsilon, will tend to a U0, which is in BV of omega and the set P1, Pn, let's say if you have n wells. And so in that case, the geometric object will be not just a minimal hypersurface, but a minimal partition. Okay, so you will have omega, and it will be partitioned in okay, P1, P2, P3, P4, and And U0 would minimize so it minimizes what? It minimizes the length of the interface or the area of the interface if you're in higher dimension, weighted by these dij's. Okay, so it minimizes the sum for I strictly less than j and of dij times. So it will be the okay h minus 1 measure if you want. So if omega is in dimension n, but I already used n, so h n minus 1 of the set where u is equal to pi intersected with the set where u0 is equal to pj intersected with omega, of course. You don't count the boundary portions. Okay, so so of course this should be made a bit more precise. You have to consider the reduced boundaries of this set, intersect them, and okay. So that was gamma convergence. And I should say that at least from a mathematical point of view, this approximation, especially for partitions, so minimal partitions are not a simple object, for instance, to compute because you have these intersections. You know, it's not very easy. And whereas this functional is something very nice to minimize, you just have to put it in a sort of pre-built numerical machine, and it will minimization will happen, and you will get a solution. So it's useful already as a numerical scheme for computing minimal partition. And it's been used by Edouard Houdet, for instance. He has beautiful images of numerical simulations using this type of things. And in fact, it's also very useful from a theoretical point of view because, well, you know, it's a recent tendency in geometry to try to construct geometric objects using a min-max method. Like, for instance, well, there are all sorts of examples. And min-max methods are quite complicated if you use the geometric objects themselves. You have this Allen-Cahn-Pitts theory, which is very complicated. But if you regularize things, then it's easier to do min-max on such functionals. And in fact, it's been successfully done in some examples, but not with this example, I think. But we hope to do it maybe someday. Okay, so that was just for motivation. And now I would like to stress, so maybe non-mathematicians in the room find that gamma convergence is something very abstract, if you want, very ad hoc. And so you might want something more concrete. So I will be very brief on this, but you also have the problem of finding limits of solutions to the Euler-Lagrange equation, which I put here. So, of course, if I had a 1 over epsilon squared, then I would put a 1 over epsilon squared here. And so you might want to look at limits of solutions to this equation, which is already something more concrete than gamma convergence of the functionals. But this is a much more complicated problem. So whereas Modica-Mortola was in the 70s, in the scalar case, so I will not write any precise hypothesis or anything, but the similar result, if you want, for limits of solution was worked out by Okay, so Ilmanen in the parabolic case, and Hutchinson and Tonegawa in 2000. By the way, I was told that it was the most cited paper published in Indiana Journal. But okay, so and in the vector case, so in the vector case, vector valued case, so there is a relatively recent paper of Fabrice Betuel in 2020. So just to give you an idea of the difficulty, so it's a more than 100 pages paper, which is published in ACTA, and it deals with the case n is equal to 2. So 2 space dimensions only. So you see that solutions, it's more complicated than gamma convergent. But so the main subject of my talk is if you want, a middle thing between solutions and gamma convergence. So you need to have a bound on the energy. And otherwise, I think that's it. And so in the case of actually in both cases, so in this case, you can have several wells also. Here you have 2 wells. And so you find a stationary varifold. So some very weak no. No. Yeah, so you see there's a big gap between the two cases, and I will say what is the main difficulty when you go to the vector valued case versus the scalar case. Yeah, so a compromise between the two things would be to look at minimizing entire solutions. And in fact, in many nonlinear problems, these solutions serve really as a building block for many results. So you're going to look at solutions. So what are they? So there are solutions of Laplacian U equal gradient W of U in R to the n in the whole space. So that's for the word entire, and they are minimizing. So such that if you take a compactly supported perturbation of U, then it has greater energy. Such that if the support of V, say, is included in a ball of radius R, then the energy of U plus V in the ball of radius R, so you cannot take the energy in the whole space can be infinite, but this will be greater than or equal to the energy of U in the ball of radius R. And so the fact that these solutions are defined in the whole space allows to blow them down. Okay, so for any epsilon, for any epsilon, you can define. So if U is a minimizing entire solution, okay, then you can define for any epsilon positive U epsilon of x equals u of x over epsilon. Okay, so that means you blow down the picture. And gamma convergence results tell you that u epsilon will converge to some u0, okay, which will be, of course, defined on the whole space and with values in the set of wells, okay? And moreover, so u0 now will have an extra property because it's the limit of blowdowns. So you can hope that u0 is zero homogeneous, okay? So it will go from Rn to the set of wells. It will minimize minimizes perimeter, or it will be a minimal partition if you want. Yeah, 0 is a minimal partition. And okay, so the last thing which should allow you to classify things is that u0 of lambda x should be equal to u0 of x for any positive lambda. So that would be, so it's something which is very intuitive if you think, okay, so I have a picture, I blow it down, then I have something which is constant along the rays. So it's very natural, but so this is something which is easy to prove, well, easier to prove in the scalar case, because mathematically it's proved using a monotonicity formulae. And in the scalar case, you have a monotonicity formula. And in the vector valued case, you don't have a monotonicity formula. So that's really a problem. Okay, so what is known? But anyway, if you believe this, you could make a wild conjecture, which would be well, in fact, it's not a conjecture, it's a question because it's true in some cases and not true in some other cases. But you could say that, okay, I have the set of minimizing entire solutions. Okay, I have the set of, let's say, minimal, I will call this a minimal cone, if you allow me. You have the set of minimal cones. Okay, and now I have a bijection between the two, and the bijection is just the blowdown limit. Okay, and if I want it to be a bijection, I have to quotient this by translations, because if you translate something after blowdown, you get the same thing. Yes? Well, it's just a shorthand for this. Minimal means it minimizes, it's a minimal partition if you want. Okay? So that's a U0. So it's a minimal cone. It means that it takes values in the wells. That it minimizes interfacial energy on any compact set. Yeah, minimizing. Yeah, really minimizing on any compact set, and that it is zero homogeneous. And okay, so that's a legitimate legitimate question. So what is known in this regard? So in fact, in the scalar case, it's very much linked to the Di Giorgi conjecture, and at least it's true. So it was proved to be true by Savin. So you have a result of Savin, which dates from, I don't know, 2009 maybe, something like that, which says that if the dimension n is less than or equal to 7, I think that because there's a difference between the hypothesis for the de-Giorgi conjecture and for minimizing entire solutions, but he proved that if n, at least until dimension 7, u is a minimizing entire solutions, implies that in fact u of x, let's say x1, xn. So if you choose coordinate system in Rn which is suitable, in fact it's just zeta 1, 2 of x1. Okay, so it's something which depends only on one variable, and so the blowdown of this is going to be just half plane. So you would have u0, the blowdown limit u0 would be u0 equal p1 here, u0 equal p2 here. Okay, so this is the x1 axis. Okay, so and until dimension 7, minimal cones are exactly hyperplanes. Okay, so you get a perfect bijection. Okay, minimizing entire solutions correspond exactly to minimal cones. Okay, so after dimension 7, it becomes more complicated because you have other minimal cones. You have the Simon's cone, and okay, so that's another problem. Okay. Yes? Yes, it's false in higher dimensions. Yeah. So this was proved. So in fact, you have two things. You have the de-Giorgi conjecture, which has different hypotheses. So your solution is not a minimizing entire solution, but satisfies some things at infinity. And then you have the other possible hypothesis that you have a minimizing entire solution. So that's two different things. But this hypothesis on the solution is something which extends very naturally to the vector valued case, whereas the hypothesis of the de-Giorgi conjecture has no clear equivalent in the vector valued case. So I would say that classifying minimizing entire solutions, to me, it's the natural generalization of the de-Giorgi conjecture to the vector valued situation. Okay, so speaking of the vector valued situation, okay, so the I have 5 minutes, that's it? Roughly 10 minutes, okay. So in the vector valued case, okay, so the simplest example would be a W. So let's say K is equal to 2. Okay, so W goes from R2 to R2. Okay, and you could say, so in that case, of course, if you have two wells, so it's not that interesting. Well, it's interesting, but maybe you want something more. So you're going to assume that you have 3 wells. Okay, P1, P2, and P3. And so we want the situation to be as simple as possible. And so we're going to take a space dimension, omega. So omega is R2. Okay? So this 2 is not that important. You could take a different K, but this one is important. It makes things much simpler. And you're going to assume again that you have the strict triangle inequality. Yeah, R-valued. Thank you. Plus a strict triangle inequality between the dij's. And so in that case, you can classify the minimal cones if you want. So you have first, so what can be the possible limits? So U0, it can be constant. Which is any one of the wells. It can be a half plane. So it could be Pi, Pj, something like that, separated by a line, which is not necessarily vertical, of course. Or it could be, so the new thing which happens is a triple junction. P1, P2, P3. Okay, and the angles here are determined by the values of the dij's. Okay, and if the triangle inequality is not strict, then it means that one of the angles is 0. All right. So, of course, you have minimizing entire solutions which converge to a constant. Take a constant. You have minimizing entire solutions which converge to a half-plane solution, if you want. And so this is a limit of... Okay, so this is a blowdown of zeta ij. Okay, the heteroclinic connection between Pi and Pj. And so the question is this the limit? Is this a blowdown limit of something? Okay, so Nicolas Fusco knows very, very well this problem, I guess. Because, so it's a problem that remained open for some time. So there was in this direction, so there was a paper of Bronsard, Schatzman, and Guai, who proved that there exists, so for symmetric W, so you take a W which has 3 wells, but which has a threefold symmetry. So they choose a nice W, and they prove that there exists an entire solution which blows down, excuse me, to the triple junction. I will call this TJ, the triple junction. Okay, and then there were many, several papers by Nicolas Fusco and Nick Alikakos, sometimes together, sometimes no. Ah, it's Giorgio Fusco, it's not you. Ah, okay, okay. Sorry about that. So Fusco, Giorgio Fusco, and Nick Alikakos, who worked sometimes together and sometimes separately, and who extended this type of construction, this construction, in a very general. In a very general way. And there's a book by Fusco, Alikakos, Fusco, Smirelnis, about this subject. But these are symmetric potentials, and they're solutions which are minimizing in a symmetric among symmetric maps, but not minimizing in the not really well. We don't know whether they are really minimizing. And so a couple of years ago, we obtained with Peter Sternberg and Allikakos and gang obtained the same result independently. Sternberg and myself and Allikakos gang. We proved that in fact, for any W, well, satisfying the hypothesis I showed, but no symmetry assumption, there exists a minimizing entire solution which blows down, to triple junctions. And in fact, as a byproduct of our proof, we also proved that if a minimizing entire solution U blows down to a half plane, then in fact, after choosing a right frame, a right system of coordinates, in fact, we have u of xy, which is equal to zeta ij of x. I recall that we are in two space dimensions here. So if you want, this is an extension to the vector valued case of the result of Savin, but dimension 2 is much easier from a geometric point of view, of course. Okay, so I guess I'll stop here. Or maybe I have 1 minute. Okay, so maybe I just want to give to talk about the result we obtained with Lia Bronsard recently. And of course, as we are researchers, we have to go beyond these hypotheses. So we try to look at the case where you don't have a strict triangle inequality, but where you have an equality like this, D13. So this is exactly what you would get in 1D if you had a 1D triple well potential. So it would do this. Okay, you would have P1, P2, P3. But to go from P1 to P3, you have to go through P2. Okay, so the distance, the energy needed to go from P1 to P3 is the sum of the energies needed here. But of course, you could imagine a vector valued situation in which the same is true. That means the minimizing path from P1 to P3 goes through P2. So this is what the situation we looked at. And we proved that if you have this condition plus some, let's say, generic hypothesis for W, for instance, that the heteroclinics are unique, etc., this type of thing, then there does not exist there does not exist a minimizing entire solution which blows down to this thing. Okay, because if you look at minimizing cones in this case, okay, so as I said, one of the angles in the triple junction becomes equal to 0, and so the only minimal cones are P1, P2, P2, P3, P1, P3. But what we prove is that this one cannot be achieved as the blowdown of a minimizing entire solution. Thank you.
Okay, so maybe we have time for a quick question. There is one.
No, vector valued case. Yeah, I think the scalar you should be able to do it with minimal effort. Yeah. Yes, there is a solution which connects P1 and P2. Yeah. No, there is none.
Okay.
In the triple junction case, can you somehow quantify in terms of the distance from the triple junction, how close you are to the heteroclinic connection? So
okay, so we did not really investigate this with Peter, but I think maybe Alikakos and gang did. But in any case, in this vector valued situation, because the potential is non-degenerate at the wells, once you're in the neighborhood of the well, you know that you have exponential convergence. So if you, let's say if you have a ball of radius r somewhere, and you know that you're close to one of the wells in this ball, then you are exponentially close as you get away from the boundary of the ball.
Along the lines
Yeah,
of the...
but what I mean is that you can take, you know, if you have this triple junction in the limit, then you can take balls of larger and larger radius, okay, that they will be included in a PI area, and then you can show that you have this, see what I mean? Yeah, so you can bootstrap.
Okay, so we thank Etienne again for the talk. Okay, so we continue with the last speaker of today, is Xavier Lamy, and he will talk about rectifiability of entropy production for weak solutions of the 2D eikonal equation with supercritical regularity.
Thank you very much for the introduction. Thanks a lot for the invitation and the organization of this very nice workshop. So, okay, let me write the title again. So, concentration, or maybe it's not even exactly the title, but it's going to be the new title, concentration of entropy productions. For the 2D eikonal equation. This is joint work with Elio Marconi, who is in Padova. And okay, from the title, it looks like it has nothing to do with micromagnetics. In fact, I will start by giving you a few motivations, which are actually a bit related to micromagnetics. And then I will come to why we are interested in these objects and what we can say about them. So all along, we will have a domain in R2, a nice domain, you can think a disk. And a map, a vector field on this domain, right? Which I call M because you see, you can think of it as maybe some kind of magnetization. And there is this energy that was introduced by Aviles and Giga, I think in 1986. Which looks a lot like the one of Etienne just before, but you will see that it will behave very differently, which is like that. So in fact, it looks exactly like the one of Etienne, but you will see what's different. Energy of M is the integral of epsilon grad M squared plus 1 over epsilon 1 minus M squared dx. And I'm going to impose also, so I have a constraint that all my vector fields that I'm looking at should be also divergence free. So Lucy, you see it's basically like, again, this, so there is this scaling parameter epsilon, which is the length scale. You can think of it as the length of transitions. There is, again, this Dirichlet energy. And there is this potential, which is, it's also a double well. Somehow it has +1 and -1 as zeros if you were R valued. But actually, no, it's because you are R2 valued, the well is the whole circle, right? So, okay, some people would call it Allen-Cahn energy or Ginzburg-Landau or Modica-Mortola. But here, the kind of the big difference is also that you assume and you impose that your vector M is, your vector field is divergence free, which, since we are in 2D, and okay, I assume, for instance, my domain is simply connected, is exactly the same as saying that M is the gradient of a scalar valued function. So you could also think of this as a second order type of Allen-Cahn. And I think this is rather in this way that they introduced it there. And this way, when I write it this way, is more related to micromagnetics in a sense. Because sometimes you see in micromagnetics, you have something like that, the exchange energy. Then you will have maybe the stray field energy that penalizes the divergence of M. And okay, if you are in a nice regime, then the divergence of M will be penalized a lot. So okay, there is a relationship. And okay, you can think also that there could be some boundary conditions which will not really be important for what I will tell you, but just to fix some ideas. Some common boundary conditions are to require that M is normal to the, is tangent to the boundary, so it has scalar product with the normal, which is 0, which is supernatural if you think about micromagnetics, because this is exactly the same thing as requiring. So this divergence is 0 in omega, but if you think of M as extended to the whole R2 with 0 outside, then my boundary condition is exactly like asking that the divergence of this new vector field is 0. And this is typically what you have with the stray field, right? So I mean, a control on this thing. Okay, so in that paper, they have a conjecture, which is still open. Let me call it 1D energy concentration conjecture. Which is in fact a conjecture about gamma convergence, but let me state it just about minimizers. But for people who know what gamma convergence is, then you can make the similar conjecture for gamma convergence, which is to say, okay, if M epsilon, okay, obviously, maybe I didn't say it, epsilon is a small parameter, small and positive, right? If M epsilon minimizes the energy E epsilon, then, okay, along a subsequence, I will never write my subsequences, but it should converge to some map M. And here, I don't even say exactly in what topology, but later I will say more about that, which will be divergence free. Also, you cannot expect that your limit, since when epsilon is small, you are penalizing values that are far from S1. You expect that your limit will be S1 valued. And the conjecture is about what the energy converges to. And it says that it should converge basically on a one-dimensional jump set of your function M. So let me write it like that. A constant, M plus minus M minus to the cube. And then you integrate this with respect to a one-dimensional measure. So here, let me say what I mean by jump set. Those would be all the points in omega, which are such that when you do a blow up around that point, what you see is basically just two constant states separated by a line. So that so u of x plus ry, when r goes to 0 in say L1 lock with respect to the y variable, and this is M, it should converge to something like is a straight jump, and you have two constant values on both sides, right? So, I mean, you can always define that set, the set of points where you have this nice property. It is always a set on which you can integrate with the one-dimensional measure. And the conjecture says that this is where the energy should concentrate. So maybe, I mean, here, this thing of sending R to 0, what you have to think about is really like, as in the picture of pictures of HN, like you would have some smooth values on one side, smooth values on the other side, and when you blow up around the point, it's like zooming in, and you see something that is straighter and straighter, right? And in some sense, this is exactly the same thing that Etienne had, except in this case, the two wells were +1 and -1. So this thing was just integrating 1, and it was the perimeter of this jump set, right? Here, what changes is that my M, it takes values into the circle. So now, I mean, I could have very small jumps that accumulate, and the cost I pay for that is just the cube of the jumps. So this is why at the end the model is very different, because this expected limited behavior is something that allows a lot of jumps to accumulate much more than in Etienne's setting just before. It's a cube. Yeah, sorry, it's a cube. My 3 looks like a 2, sorry. So here, this picture is really, I'm meaning a constant state on the left, a constant state on the right. This is when I blow up. And here, of course, it's not constant, but you imagine it's smooth on both sides. And once you blow up, you see constants. Is that clear? So, okay, I wrote down this conjecture for minimizers, but I mean, the full conjecture is that this energy gamma converges to that one. And it's actually surprisingly hard to solve this conjecture, and no one knows how to do it. So, I mean, these results I want to tell you about are like a very small step in that direction. Right, so this, like, you could have configuration with vortices or stuff like that. This is what you mean. They cost no energy in that energy scaling. So you can have them, but just they correspond to 0 energy states in the limit. So, and in fact, that's one of the issues. They can be there, but somehow they're not controlled by the energy. So, I mean, they are counterexamples to a lot of statements you could try to make about these things. And basically, what's the main obstacle? No, minimizers are just will be so okay, so sorry. I guess I was maybe not clear. I mean, here, for every point in the jump set, for every fixed x, you have a different, I guess maybe that was your question. For every fixed x, you have a different values when you zoom in. Yeah. Sorry, that was your question, right? I misunderstood it. And here again, this is like, for every fixed x, I do my blow up at a fixed base point with respect to the y variable, and I get this. So no, there is no reason why they should be constant. Okay, why is this thing somehow harder than the Modica-Mortola statement? Is because we don't really have nice properties of our limit objects. So like the structure of limits of these things, again, limits along a subsequence of limits of any sequence of bounded energy. For instance, when you look at this energy, it's not even clear that your limit will be S1 valued. And because it's not clear at first sight that you will have a strong enough convergence. And in the Modica-Mortola setting, the limits would be BV. And once you are BV, you have very nice properties relating the jump set of the functions to many things, and this is the main difference in this problem. And for those who know the BV space, when you see this cube here, you understand that you will never have BV control here, but I will come back to that. Anyway, the first things that people said about the structure of these possible limits, it goes back to actually this is a PISA story for some part. There's that paper by Ambrosio De Lellis Mantegazza. It's 99. Around the same time, De Simone, Cohn, Müller, and Otto proved a very similar result. The first thing is that you have this, the convergence is actually strong in L1. Okay, once you have convergence of a subsequence, say in distributions, it's actually strong in L1. And so this enables you to pass to the limit in this S1 valued constraint. So you get that your limit is a solution of these two constraints here, right? It should be a divergence-free vector field with unit norm in omega. Okay, let me call this E. And this is the eikonal equation in my title. Maybe for you, the eikonal equation is something else, but in fact, this is just a 2D way of writing the eikonal equation. If you write that M is the gradient of U rotated, then it's the actual eikonal equation that you probably know under that name. So in 2D, this is the same thing, right? Okay, so that's one thing. At least we know that our limits, they are solutions of this equation. Of course, this divergence is in the weak sense, right? So, okay, what do we know about solutions of this equation? So let's talk a bit about like solutions of weak solutions of this equation in general. So if you take a smooth solution, it's like very, very rigid. Why is that? Because in fact, this is a hyperbolic equation, and the solution has to be constant along some characteristic lines. So typically, you know the value of M at one point, then in fact, on the orthogonal line, it must stay the same. So in fact, basically, then you can determine, if you know some boundary data, you determine completely your solution. But in fact, it's actually not good because it could happen that this characteristic cross, and then you have an issue, right? You actually, in general, you don't have smooth solutions. So these smooth solutions, they are very rigid, but they are just too rigid, right? And here, the solutions that you get, they are just weak solutions. So weak solutions, let's do an example. An example is this type of objects, right? You just take a constant jump, right? A constant value m minus on one side, m plus on the other side. And as long as the tangential component, the normal component is continuous, right? So here you have a normal vector here to your jump set. As long as the normal component is continuous, is the same, this is actually a weak solution to this equation, if those things are S1 valued constants. So I mean, those ones we like, because this is the ones we want to see in the limit. But actually, they are extremely flexible, the weak solutions. An example of that is that if you look at the set of functions, Lipschitz functions that have gradient of norm 1, this is actually dense in the sets of one Lipschitz functions for the, say, the uniform convergence. So this is like a baby version of this H principle and convex integration business. So in fact, I mean, this is telling you that you take any Lipschitz function, you can approximate it in some way with solutions of this equation. So I mean, if this is really the setting we are completely screwed, right? There is no way we're gonna be proving a nice structure result like that. Luckily, what this energy approximation does for us is to select a subclass of weak solution.
So here, what happens is that the selected solutions, they must have finite entropy, and I will tell you in a second what this means. This means the following, is that actually you can, so you take your solution M, you take some nonlinear function of it, vector field, you take the divergence of it, and if this person here is nice enough, I will tell you in a second what it is, then, okay, you don't expect this to be 0, but at least to be somehow to have some control, and in that case, the control is that it should be a finite measure. So here, I mean, I'm saying basically that it has like a bounded integral, but in fact, it could also be a measure. It doesn't need to be L1 for all phi, which are in the set of entropies. And what are entropies? Entropies, okay, there is a definition, like you take smooth vector fields on the circle, which have this property that if you take their derivative along the circle, what you get is a tangent vector to the circle. So here I'm saying I have my circle, I look at the values of phi, and I look at the derivative of phi along the circle. What I want to get is a vector that is tangent to the circle. And okay, this may look like an arbitrary definition. The main interest of that definition is that if you take a smooth solution, so what will happen is that actually these divergences, they will be 0. Okay? So if you have a smooth solution, these objects are trivial. So you can look at them as somehow measuring how singular a solution is. And that's what's interesting to us. Like if you're smooth, this is 0. And if you start having bad singularities, this will be bigger and bigger and wilder and wilder. So let's look. So okay, smooth solutions, you have no entropy production. What about a jump solution? And the jump will really be like our main example to understand things in this talk. So again, this is like you have just said J. It has a normal vector. You have a constant, but different constants on both sides. Then actually, it's just an exercise about distributions to compute what this is for a general phi. And this is like basically you look at phi at m plus minus phi at m minus. You dot it with nu. And this is only supported on this jump set, and this is multiplied by the one-dimensional measure on the jump set. And actually, once you understand smooth solutions and pure jumps like that, you also understand BV solutions. So basically, this formula would also work if M is BV by the chain rule for BV functions. In that case, there is really a book by Nicola Fusco about BV functions. Right, but again, I mean, somehow we don't expect our solutions to be BV. So, so somehow understanding these things better is kind of understanding how to do a chain rule, but in a non-BV setting. Let me just say a few words about why, in our case, we have this property. It's basically because we have a control. Okay, so you take divergence phi of M, its absolute value. This is actually a measure. You take the supremum over all entropies that are bounded in C2. This you expect to be controlled. I mean, you know it's controlled by the limit of your energy densities, basically. Okay. So this supremum should be understood as the supremum of measures. And if you take a bounded energy sequence, oh, I erased it, bounded energy sequences. So this is if m is the limit of m epsilons, and they are and the actually okay. This is a void statement if the energy is non-bounded, I guess. So yeah, this is somehow like the natural objects that you control when you control the energy. And what we want to try and understand is how much it restricts the class of weak solutions so that we can actually have some kind of structures among them. Well, I'm not sure I'm doing this in the good way, but anyway. So of course, when you see this control, now you can ask like there is a new conjecture, which is a bit weaker than the first one. We call it a sub-conjecture. Is that, okay, if the energy concentration conjecture is true here, it means that those objects here, which are lower, should be also one-dimensional, right? So the sub-conjecture should be that, let me call it like 1D entropy concentration. Oh, by the way, maybe I should say why I call them entropies. It's because this idea of using these renormalizations, like looking at all vector fields, which give you new conservation laws when M is a smooth solution. This is something that comes from scalar conservation laws. There is a theory by Khrushchev about this. And there, like, there is a time evolution, and you're really looking at some kind of objects that, give you like information about the singularities as time evolves. Anyway, now the new, like the sub-conjecture is that this thing should be concentrated on the jump set, which means if I restrict myself to everywhere but the jump set, I should see 0. Yeah. Okay. And actually, then the theorem we prove with Helio, it goes in that direction. It does not completely settle it, but it just leaves a borderline case open. So let me say a bit what is known about this part of the entropy production outside the jump set. There is a structure result by Camilo De Lellis and Felix Otto in 2003, I think, which tells you a little bit about this. Somehow it says that, again, the same object, they don't know that it's 0, but at least it is orthogonal to the one-dimensional measure, which is telling you, okay, what does it mean? This means that if I take a one-dimensional set and I plug it in this measure, it gives 0, right? The measure of a one-dimensional set by this thing is 0. So this is telling us that this measure is somehow more diffuse than one-dimensional, right? So the part outside jumped is more diffuse. This is what this result is telling you. And it's really about saying, okay, if I have a part of this measure that looks one-dimensional, then in fact it has to be around the point that is a jump point of M. So this is kind of a quite deep structure result about these objects. Let me also say that the sub-conjecture has been proved in a very related case about similar questions about Berger's equation by Helio, my co-author on this thing. I won't have time to enter the details. What is the setting for Berger's equation and what's the difference with this? But for Berger's equation, it's settled this concentration property here, but not the gamma convergence one. Okay, so now this is what we want to understand, right? There is one case where we know it's true. It's in the BV case, right? This is this chain rule property here. We saw that the entropy production is concentrated on the jump set. So yeah, this is actually part of their structure result. On the jump set, you can really say that it looks like that. So okay, the jump set, if you define it like that, it is always rectifiable. But of course, here the whole point is that if you define a set that is one-dimensional as the one-dimensional concentration set of this measure, you want to say that this is the same thing at this jump set here. And this is what this result is about. So this is the non-trivial thing in that result. Okay, so again, I said this already, but if M is BV, then basically you get this concentration property because you have the chain rule in BV. And BV, okay, maybe I never said it, I should have, is the set of all maps whose derivative distributional derivatives are measures. But let me write it in a slightly different way. You can also say that it's the set of maps such that when you look at increments and you divide by the norm of the increments and you take the L1 norm, okay, in the set where, so that the increments do not leave your omega, then this should be bounded, okay. I'm writing it, this is equivalent to being bounded variation. I'm writing it this way so that we can compare to the type of assumptions I will ask for in a second. So I told you several times that our solutions, they won't be BV. And in fact, we know exactly what type of regularity they have. So somehow, I mean, if all our solutions were BV, I mean, we would be done, right? But this finite entropy property is actually equivalent. So the solutions that we're interested in is equivalent to being in some Barbarian Bezoff space, which I'm going to write some signs, but then you're going to see that it's actually very easy to understand. So this B1/3 infinity. What does it mean? It means I have 1/3 of derivative in L3, in some sense. And what it means is actually the supremum over all h's of M. So I do my finite difference of M. I divide by h to the 1/3 now. This is my 1/3 of derivative. And I look at this in L3, again on the right set. And ask for this to be finite. Okay, and this 3 is actually really the same 3 as this one, as you might guess. So you see, I mean, this is not the same space, right? We have functions that are here, that are not here, so there is really something to prove. And in some sense, I mean, the whole game is to go beyond BV, right? In BV, we have the chain rule. It's not a trivial thing, but it's known. And we want to lower the regularity, right? And let me introduce some intermediate spaces. Which are supernatural. I just interpolate between my 1 and my 3 here. You have that, okay, BV. Actually, all my functions, they're always L infinity because they take values in S1, right? You can embed it. So you have your final thing here. This B1/3, 3 infinity. And inside you can take any B 1 over P infinity for any P between 3 and 1, which would be that, I mean, the finite quantity in this space. Maybe you can guess what it is. It's the supremum where I look at my finite differences. I divide by the increment to the 1 over P derivatives. I take the LP norm, and I want this to be bounded. Okay, so this is like a very natural interpolation between BV and our space. Maybe a remark that's interesting to make is that this supremum here is always larger than something that is related to the jumps. So this type of quantity controls in particular the integral of the jumps to the power p. So you see when p equals 3, you recover like this is the natural space for our energy. And now I can state our results. So this is with Helio. We put it maybe a month or two ago on the archive, which is really, I mean, somehow a two partial result, but okay, this is what we can do. So basically, if M is a weak solution of my equation, so divergence-free unit vector field with this additional intermediate regularity for some P, which is strictly below 3. So we can do all of these intermediate spaces, but not the very borderline case. Then you have the concentration. Actually, you have the concentration, but only for odd entropies. I will comment in a second about this. So this is the statement. So let me make two remarks. So yeah, this is what I said, like only the borderline case is open now, which is of course, I mean, where everything happens in some sense. But still, it's so much interesting that you can go beyond BVA and still get this type of chain rule-like result. And this restriction to odd entropies, it should not be here. It comes from our method of proof. But in some sense, it's not a big deal because to understand the gamma limit, you only need to look at odd entropies. This, I didn't tell you the story, but odd entropies are the only ones required to understand the gamma limit. So for the original conjecture. Okay, that's the statement. Now the question is, how much time do you give me to say a few words about the proof? So 5 to 10 minutes? Wow, okay. Well, I'll take just 5. Okay. So I think I'll just give a very non-technical heuristic idea of why somehow if you make that extra assumption, you expect things to be easier. Okay, so it would be ideas of proof. So I wanted to do two parts, like one heuristics and then actually how we implement the heuristics. I think I'll just do the heuristics. The heuristic is very easy. Like, okay, you start calculating things for a BV function because then you can actually like use the chain rule and compute everything. And if you do that and you look at the divergence of phi of m, so your entropy production. So okay, here if I say outside the jump set, then okay, I don't see anything else because I'm BV. So let me just say outside the jump set, but just the big jumps. So I fix a parameter delta, and I keep only the small jumps in here. Then because you have this kind of control of the jumps by these norms, in fact, it's immediate to see that you have this is controlled by delta to the 3 minus p times this base of semi-norm here. Right? There should be some power, I guess. Also here, there should have been some power. 1 over p, it was not homogeneous. So here it should be probably to the, okay, 3 over, okay, p over 3 maybe. I'm guessing something like that, some alpha. So anyway, this is what's hidden here is completely elementary, just using this and saying that if I'm looking at jumps, only the jumps that are smaller than delta, then part of it I put in here and part of it I put in this control here. Now, of course, I used a lot that I knew that I was concentrated on jumps here. But in some sense, this is telling you that, I mean, this estimate written like that, you could expect it to be true without the BV assumption. To just write down these objects, I don't need the BV assumption. And this is kind of what we hope. So in some sense, when you have this assumption that this is finite, you are kind of preventing small jumps from getting too close together. And this is kind of the mechanism that is at play here. And you could say, well, okay, then okay, if this is true in general, then you send delta to 0. And when you send delta to 0, you will have the full jump set here. And so you have proved what you wanted because this goes to 0, right? You could say, well, okay, you're doing these calculations by assuming that everything is concentrated of jumps. Of course, it's very easy. You're basically assuming your conjecture in order to prove it. But the thing is that there is this result by Elio, okay, around 2021, 22, I don't remember, which basically tells you that with this diffuse part of the entropy production, so the one that is outside the jump, you can basically think of it, or at least it's consistent. So he has a structural result about the diffuse part, which is consistent with thinking of it as coming from the accumulation of infinitesimal jumps. Okay, and if you believe that kind of things, and you believe that this kind of estimate is telling you that you cannot really accumulate two small jumps, well, okay, at a very heuristic level, you are kind of in a good shape to show your concentration result. I guess I will stop here. I will just say two buzzwords to, I mean, this is not the end of the story. Actually, you need to make this rigorous. And for this, there are quite deep technical tools, which are a kinetic formulation of our problem and Lagrangian representation of our solutions, which this Lagrangian representation is in some sense also a Pisa story because it's very much inspired by this superposition principle of Ambrosio for the continuity equation. And I would have loved to tell you about these objects, but I won't do so. I will stop here.
Okay, thanks for the nice talk. Are there questions? Okay.
Where's the 3 coming from in the estimate?
Because these things, this is something I erased, but basically they are controlled by the energy, right? And here, when I write this, I'm assuming BV. So this thing is basically the sum of the jump to the squared, to the power 3. So yeah, here inside. So I told you this thing is controlled by the energy. And in BV, you know already that everything is concentrated. So you have like, this is like the integral of the jumps to the cube, sorry. Right, so this is, and so if I know that so I write that this is like this 3, I write as 3 minus p plus p, right?
Yeah, okay, yeah.
And here I was looking only at jumps that were smaller than delta. So I take part of it, I put it in this delta to the 3 minus p. Part of it, I put it here, and I estimate it.
Okay,
so actually this
thank
is
you.
p here. This alpha is p.
Okay.
Yeah, so if you don't look at gamma convergence, but just convergence of minimizer, can it help in any way?
in some sense, it helps if you have special cases like special domains, special boundary conditions where you know the minimizer. So if you know that the minimizer has this property of concentration, you can hope to go a bit further. And the best is actually the only thing that's known is if you know the minimizer is BV, then you can go ahead and prove basically the upper bound and get convergence of minimizers. So for instance, if you are in a disk with this tangential boundary, always with tangential boundary condition, if you are in a disk, then the minimizer of the limit energy is just a vortex, basically. This is like this. And it has, it's BV, right? And so here you can prove the convergence. And there are other cases like this stadium-like domains or ellipsoids. You can basically the minimizer has just a single line of singularity here. It's basically the gradient of the distance function to the boundary. And in those cases, because you know the minimizer of the limit problem is so nice, you can go back and prove it's the limit of minimizers. And in micromagnetics models, at least there is this thing of this paper by two papers by Riviere and Sarfati. And okay, their model is a bit different. And in their case, the minimizers are always viscosity solutions of the equation, and those are always BV. So in their case, they can prove convergence of minimizers, but still the gamma convergence is not clear. So they don't have convergence of near minimizers, if you like.
Okay, other questions?
Kind of solutions that you're showing here are known as Vandenberg construction in micromagnetics.
Ah, okay.
Yes.
Vandenberg. Okay, thank you. Right. Mm. Mm-hmm. Right. But actually, I mean, it's, yeah, you need to show so that they minimize your limit energy, right? Which is. Yeah. Mm-hmm. But for instance, if you take a square, then your candidate minimizer would be something that has a singularity like that. And here we cannot show the convergence of minimizers.
Even if it's BV, even if it's BV also in that case, no? The minimizer.
Yeah, because you cannot show that this is the minimizer of the kind of conjecture limit problem. So if you could show that this was a minimizer of your limit energy of this integral of the cube jump, then you would get a proof of that minimizers converge to this.
Okay.
If instead you have P less than 3, then you have convex integration in this stream?
You mean in my initial energy or
in your condition regularity, let's say, instead of okay, the energy gives you 3, but assume that you have the regularity with P less than 3, then you can do anything you want? Or...
So I guess it will be
so like you take a solution of the eikonal equation and you substitute like the entropy conditions, the energy condition with the base of yes.
Yeah, so okay, this is really like for convex integration, this is one of the simplest models of convex integration, right? You have a bunch of, I mean, basically every connection is rank 1 because you're scalar.
Exactly.
But still, I don't know how precisely you can, I mean, you know this better than me probably, how precisely you can estimate the regularity of your approximate solutions that you construct.
Exactly.
I guess this is kind of
because it seems like Euler. I mean, I don't know. Like that P equal to 3 is like the.
In fact, this okay, I erased it, but I mentioned that this finite entropy condition is completely equivalent to this base-off regularity. One side of this is the easy part of the Onsager conjecture, like you do this commutator argument and you.
Like yes, I mean above 3 you would have energy conservation, so you have more.
Yeah, above that your divergences will not even be measured.
Exactly.
In principle, white thing could happen, but just in principle. Then if you actually want to construct them and monitor the regularity, I don't know.
Yeah.
Other questions? Okay, so if not, we thank Xavier again.